Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Before we set sail among the stars, we must first sense the shape of the ship that carries us. The Milky Way, in all its splendor, is built upon an invisible architecture. Like an elaborate cathedral shrouded in fog, its grand design is partly hidden from our eyes. What holds up this starlit city? What scaffold keeps our galactic home from flying apart? To answer, we venture beyond the visible, into the domain of the unseen, a realm of gravity and ghostly matter, the invisible architecture that underpins the galaxy. Imagine a vast, dark scaffold woven from something we cannot touch or see. A web of gravity, shaped by a mysterious substance known as dark matter. We call it dark, not just because it emits no light, but because it eludes direct detection, hiding in shadows beyond our instrument's reach. And yet, though invisible, it is immensely real. It sculpts the galaxy's form and governs the dance of the stars. If we could don magical glasses to see mass instead of light, we would behold a gigantic halo enveloping the Milky Way, a roughly spherical cloud stretching far beyond the galaxy's shining disk. This halo, mostly made of dark matter, is the invisible architecture, the foundation on which the visible Milky Way is built. We feel its presence through its pull. Just as a steady hand might guide dancers on a floor, the gravity of dark matter guides the stars in their orbits. In the outskirts of the galaxy, far from the brilliant core and spiral arms, stars and clouds of gas whirl around the center at astonishing speeds. Logic suggests they should drift away into the depths of space. There simply isn't enough visible mass in stars or gas to hold them. Yet, they remain bound, as if tethered by phantom strings. These tethers are the gravitational grip of dark matter, an unseen mass whose influence permeates the galaxy. It forms an invisible halo, extending hundreds of thousands of light years beyond the edge of the visible Milky Way, cocooning it like an unseen guardian. This hidden architecture doesn't glow or sparkle, but it makes itself known in other ways. Picture the galaxy like a vast, spinning carousel. In a normal carousel, things at the edge move more slowly than those near the center. But in our galaxy, stars in the far suburbs orbit at nearly the same speed as those closer in. It's as if the carousel's rim has extra hidden weight, providing the needed gravity to keep those outer stars from escaping. That extra weight is dark matter. It is the silent partner to all the shining stars, outweighing them many times over. For every star we see twinkling in the Milky Way, there is far more mass hiding in the dark, perhaps 5 to 10 times more. This dark mass forms the scaffold, the architecture without which the beautiful glowing disk of our galaxy would not exist as we know it. But dark matter is not the only component of the invisible architecture. Gravity itself is the architect, the master planner that molds matter into structure. Long ago, before the Milky Way even had its name or shape, gravity drew together a diffuse cloud of matter. It began to pull everything inward, spinning and flattening the gathering material. Like an artist shaping clay, gravity sculpted the first outlines of our galaxy. It made the wispy tendrils of primordial gas collapse into denser clumps, igniting the first stars. Over billions of years, it orchestrated mergers of smaller protogalaxies, each merger guided by the gravitational hand of dark matter, halos merging as well. The Milky Way grew within a gravitational cradle, an underlying framework stretching through space like the skeleton of a great beast. Even today, gravity's influence extends beyond the stars. The space between galaxies is not entirely empty. It is threaded by filaments of dark matter, forming a cosmic web. Our Milky Way lives at the intersection of these filaments, like a pearl caught in a spider's web of invisible threads. Through these threads, clumps of matter, both dark and ordinary, flow inward. One might imagine cosmic tides, slow and inexorable, delivering fresh gas and even small galaxies toward the Milky Way. This ongoing infall continues to shape our galaxy, guided by the unseen architecture of the cosmic web. We drift in a gentle current of gravity, a river whose banks are made of dark matter. Close your eyes and picture the Milky Way not just as stars, but as an enormous gravitational presence. Feel the invisible arms that extend far beyond the furthest star, reaching out into intergalactic night. This is the scaffold that holds us, the container of our existence on a galactic scale. Stars, nebulae, planets, and people all live embedded in this gravitational field, moving along paths choreographed by an architecture we perceive only indirectly. The invisible architecture humbles us. It reminds us that what is most important is often hidden. We live in the luminous beauty of a spiral galaxy, but that beauty is underwritten by something dark, massive, and enigmatic. The stars trust this structure. They orbit faithfully, generation after generation, as if following ancient roads built by an unknown engineer. We too are sustained by this invisible framework. Without it, our sun might wander off into the void, carrying Earth and us with it into solitude. Instead, we remain part of this grand rotating city of stars, anchored by a dark, unseen sea of gravity. As our journey continues, keep this concept close to your heart. Not everything that matters can be seen. The Milky Way's brilliance rests upon an invisible foundation. In life and in galaxies, the unseen often guides the seen. We move onward now into the visible realm of the Milky Way, but we do so knowing that an invisible architecture holds it all together, like the silent knowledge beneath spoken words, or the unseen wind shaping the dunes. In this galaxy, as in ourselves, there is more than meets the eye. Anatomy of the Milky Way. Now that we sense the hidden scaffolding, let us step back and behold the anatomy of the Milky Way, the grand design of our galactic home. If we could rise above the disk and look down from far away, what would we see? We would witness a spiral galaxy in its prime, a flat disk of stars and gas, with graceful arms winding outward from a bright central region. It would resemble a vast rotating pinwheel strewn with glittering lights. This is the city of stars we call home, a cosmic metropolis containing everything we know. At the center of it all lies the galactic bulge, a rounded hub of stars that swells above and below the flat plane of the disk. The bulge is like the city center, crowded, bustling, and ancient. Its stars are mostly old amber-colored beings, many billions of years in age. Some of these stars are almost as old as the universe itself, born when the galaxy was young and the cosmos had barely emerged from darkness. The bulge is roughly spherical or slightly elongated. In fact, observations show that the Milky Way has a central bar, a long horizontal concentration of stars crossing the core. Think of it as a glowing bar of stars at the galaxy's heart, with the bulge wrapped around it. This stellar bar acts like a cosmic traffic system, channeling gas inwards and helping to form new stars and feed the central region. The bulge and bar together form the beating heart of the Milky Way, densely packed with stars dancing in complex orbits. Extending outward from the bulge are the spiral arms, the most striking feature of a spiral galaxy. The Milky Way sports multiple spiral arms, curving out like swirls in a whirlpool. Each arm is a region of higher density. Imagine waves in the galactic disk, where stars and gas get slightly bunched together as they orbit the center. In these denser waves, gas clouds compress and new stars ignite, lighting up the arms with hot, young suns that shine blue-white. Nebulae, great clouds of glowing gas, pepper the arms, marking the nurseries where stars are born. From above, the arms would appear like starlit ribbons or the tendrils of a vast cosmic jellyfish rotating slowly around the core. They have poetic names derived from constellations we see in their directions: Perseus Arm, Sagittarius Arm, Scutum Centaurus Arm, Carina Arm, and the smaller Orion Spur where our Sun resides. Our solar system is currently nestled in this Orion Spur, a minor arm or branch between major arms, about 27,000 light-years from the galactic center, halfway out in the disk. We truly live in the galactic suburbs, a quiet neighborhood between busier spiral arms. The disk itself, which contains the spiral arms, is a marvel. A broad, thin plain of stars, gas and dust, roughly 100,000 light-years across in diameter. To give a sense of scale, that is about 1e5 light-years from one end to the other. In miles, a number so large, about 600 trillion, that it defies comprehension. Yet, despite its vast width, the disk is relatively thin, only about 1,000 light-years thick in the main stellar layer. In proportion, it's much thinner than a pancake. The Milky Way is a truly flat system. If the galaxy were reduced to the size of an old vinyl record, the disk would be like a razor-thin film, and the bulge a small bump at the center. Within this disk, stars orbit the center in nearly circular paths, like billions of bees swarming around a hive. They move in orderly fashion, although each carries its own slight up and down motion, giving the disk some thickness. There are actually two components to the disk: a thin disk containing most of the young stars, gas and dust, where spiral arms are prominent, and a thick disk of older stars that extends a bit further above and below the plane. The thick disk's stars are fewer and older, hinting at a past era of the galaxy when star formation and dynamics were a bit different. Together, these disks form the galactic equivalent of the streets and districts where our tale of star life unfolds. Encircling everything is the stellar halo, a spherical distribution of stars and ancient clusters that envelop the disk and bulge. The halo is sparse. Its stars are like lone wanderers, often old and feeble in light, scattered in a vast volume. Among them are the globular clusters, about 150 tight balls of very old stars orbiting the galactic center in extended, inclined paths. These clusters are fossils of an earlier time, some formed in the Milky Way's youth, others perhaps the remnants of small galaxies consumed by the Milky Way long ago. The stellar halo reaches far beyond the disk, fading into the dark. It's the galactic countryside, mostly empty, but for those isolated stars and clusters. As we learned in the invisible architecture, this stellar halo is just the visible tip of a much larger dark matter halo that extends even farther and holds the whole system in its gravitational grip. Imagine for a moment we could view a cross-section of the Milky Way, a side view. We'd see the bulge in the middle, a central swelling of stars. Stretching out from it is the thin disk, narrow and bright, with spiral arms embedded within. Slightly puffed up around the thin disk is the thick disk, a dimmer and broader spread of stars. Surrounding everything is the faint halo of ancient stars and globular clusters. This is the layered anatomy of our galaxy, a structure as intricate as any organism. Each part, bulge, bar, thin disk, thick disk, arms, halo, has its own character and story, yet all are bound together by gravity into one rotating system. Within this grand design, our Sun is a tiny speck. It takes about 250 million years for the Sun to complete one orbit around the galactic center, a galactic year. The last time we were at our current position in orbit, there were dinosaurs just beginning to roam Earth, and the first flowers were blooming. In that time, the Sun has journeyed around the galaxy perhaps 18 to 20 times in its 4.6 billion year life. This illustrates both the immense scale of the Milky Way and the surprisingly dynamic nature of our position in it. We are moving along with the entire solar system at roughly 230 kilometers per second, over 500,000 miles per hour, just to keep up with the galactic rotation, like riders on a massive carousel. The Milky Way's anatomy is not rigid. It's a living structure. The spiral arms rotate around the center, though not like solid blades. Stars drift in and out of them. The bar in the center slowly twists. The very disk can ripple. Interactions with satellite galaxies can send waves through it, causing subtle warps. In fact, observations show our disk is slightly warped, like a stretched-out ripple, likely due to gravitational interactions with neighbors or remnants of old mergers. So one might picture the Milky Way not as a static pinwheel, but as a swaying spiral, its disk breathing and waving over long timescales, its arms a pattern in motion. To truly appreciate this anatomy, consider the unity of it. Hundreds of billions of stars, each with its own orbit, many with their own planets, together forming these coherent structural components. From our vantage point on Earth, inside the disk, we see the Milky Way as that misty band across the sky. That band is essentially our edge-on view through the disk, a cross-section of countless distant stars concentrated along the plane. The dark patches we see, like the Great Rift dividing the bright Milky Way in the summer sky, are not empty of stars, but choked with dust that blocks starlight. Those are part of the disk's anatomy too, dark nebulae that silhouette against the starry backdrop. It is humbling to realize that for a long time, we didn't even know the true shape of our galaxy. Early astronomers peering with small telescopes, or just eye, only saw that band and tried to guess our imagely in the 20th century did we map the Milky Way's spiral structure, using telescopes sensitive to radio waves and infrared light, which can penetrate dust, and by cataloging the distances of stars and clusters. Today, missions like Gaia have measured precise positions and motions of over 1 billion stars, allowing us to cartograph the Milky Way's structure with unprecedented accuracy. Yet, being inside it, we still find pieces of the puzzle gradually, like a person mapping a forest from within, tree by tree. In summary, the Milky Way's anatomy can be thought of in layers and components. A luminous central bulge with a bar, a sprawling disk with spiral arms, thin disk plus a thicker disk of older stars, and a vast halo beyond. It is a majestic aggregation of matter and stars, structured yet fluid in form. Think of the Milky Way as a great cosmic tree. The bulge is the sturdy trunk. The disk and arms are the wide branches and leaves catching the light, and the halo is the sparse canopy spreading out into the sky. Or imagine it as an island. The bulge is a mountainous continent at the center. The disk is the flat expanse of land and sea around it with spiral currents, and the halo is the thin atmosphere and lonely outlying islets. This is our galaxy's body, magnificent and humbling. Knowing its anatomy, we are ready to delve deeper into its organs and processes. We have seen the map. Now we turn to the citizens of this galaxy, the stars themselves, and how they live and evolve in this stellar city. Stellar population and evolution. Every point of light in the Milky Way is a story in itself. A star shining with nuclear fire, perhaps orbited by planets, perhaps destined to explode or fade. In the Milky Way's vast population, there are stars of all ages and sizes, from brilliant blue giants to faint red dwarfs. Stellar population and evolution is the study of these billions of lives. How stars are born, how they age, and how they die, all within the galactic community. As we traverse this topic, imagine walking through a cosmic garden where stars are like flowers at different stages, buds, blooms, withering stalks, all contributing to the cycle of life in the galaxy. Astronomers classify stars in our galaxy broadly into populations. The population 1 stars are those like our Sun, relatively younger in cosmic terms, and richer in heavy elements, elements heavier than helium, because they are born from recycled materials. They tend to reside in the disk, especially the spiral arms, where active star formation is ongoing. Then there are population 2 stars, old, metal-poor stars, fossils from the early galaxy. These often inhabit the bulge and the halo, like in globular clusters or as solitary halo stars. There is even a theoretical population 3, the very first stars born in the universe, extremely metal-poor and long gone now. but their imprint might survive in some of the oldest Pop-2 stars. In the Milky Way, stellar evolution is not just theory, it's on full display. Consider the spiral arms. They are studded with stellar nurseries where new stars take shape. Giant cold clouds of molecular gas and dust, colossal wombs known as molecular clouds, collapse under gravity in pockets, forming clusters of newborn stars. Within these nebulae, we find young protostars still accreting mass, often hidden in dust, and bright newborn stars whose intense radiation causes the surrounding gas to glow. The Orion Nebula, for example, in our Orion Spur, is a nearby region where such processes occur, and the Carina Nebula is another dramatic stellar nursery, featuring massive stars that formed just a few million years ago. These newborn stars are typically hot and massive, shining blue-white and living short, brilliant lives. They are often found in loose groups or clusters, like cosmic kindergartens of stars. The presence of such O and B-type stars in the spiral arms is what makes the arms stand out with a bluish tinge. These stars are luminous beacons, but they burn out quickly in a few tens of millions of years, and thus never stray far from their birthplaces. As stars age, they drift away from such nurseries and join the general population of the galactic disk. Intermediate mass stars like our Sun live for billions of years, orbiting peacefully, slowly using up their hydrogen fuel. They may drift around the galaxy many times. Our Sun, for instance, has gone around the center about 20 times and witnessed the changing arrangement of spiral arms and clouds around it. Over time, stars like the Sun will exhaust their core hydrogen and expand into red giants, glowing with a cooler, reddish hue but enormously larger and more luminous than before. In this phase, they puff off their outer layers, enriching the surrounding space with elements formed in their interiors. Many such aging stars can be found in the Milky Way. Look toward the bulge, and you find myriad red giants crowding the region, evidence of older stellar generations. Some stars live violent, short lives. The high-mass stars, perhaps born in those same clusters, race through their nuclear fuel in mere millions of years. They swell into supergiants, some red, some blue, depending on mass and stage. In the Milky Way, famous examples include Betelgeuse, a red supergiant in Orion, nearing the end of its life, and Rigel, a blue supergiant. When their cores can no longer sustain fusion, these massive stars die in titanic explosions, supernova, blasting their guts of heavy elements into space. Each supernova is like a brief, tragic fireworks show, outshining whole star clusters for weeks. Our galaxy has witnessed countless such explosions over its lifespan. They are part of its ecosystem. The remnants of these explosions, expanding clouds of gas like the Crab Nebula or Veil Nebula, lace the galaxy, adding to the diffuse background of matter that will one day form new stars. And what remains of the star itself can be a neutron star or a black hole, ultra-dense cinders of stellar cores that often quietly linger in the galaxy's disk or halo. Meanwhile, low-mass stars, far more common, especially faint red dwarfs that make up perhaps the majority of stars by number, live incredibly long, slow lives, longer than the current age of the universe in many cases. These red dwarfs form in the disk as well, and will burn their fuel so gradually they might outlast the galaxy's current form. These unobtrusive stars form the quiet backbone of the Milky Way's stellar population, too dim individually to notice, but collectively contributing significant mass. Stellar evolution in the Milky Way is a cycle. New stars form from gas enriched by older stars, live their lives, and then return material to the galaxy when they die. This cycle gradually changes the content of the galaxy. Early generations had almost no elements like carbon, oxygen, iron. Those were forged in stars and supernovae. Later generations, like the Sun, were born from clouds already seeded with these elements. Thus, our Sun contains about 2% of its mass in elements heavier than helium. Small, but enough to allow the formation of rocky planets like Earth. Without countless star lives and deaths before it, the Sun would have had no planets, or at least no solid ones, and we would not exist. The Milky Way's star population is thus intimately linked to everything around us, including life. The galaxy also sorts its stars by location. In the halo, we find primarily those old population 2 stars, with very low metallicity, a sign they formed when heavy elements were scarce. Many might be remnants of smaller galaxies the Milky Way gobbled up long ago. We'll get to that in galactic cannibalism. These halo stars often have orbits that plunge in and out of the disk at steep angles or swing far out, not the orderly carousel orbits of the disk stars. In the bulge, stars are again old on average, but slightly more enriched than the halo, and their orbits are randomly oriented, creating a spherical distribution. Some bulge stars may have formed in early mergers or in early starbursts in the young Milky Way. In the thin disk, we have stars spanning a range of ages, from newborns just a few million years old in spiral arms, to intermediate 5 billion-year-old stars like the Sun, to older disk stars, maybe 8 to 10 billion years old. The thin disk tends to host stars with higher metallicities, meaning each generation has incorporated more of those heavy elements. The thick disk stars are older, maybe 10 to 12 billion years, and have lower heavy element content. They might be the remnants of the early disk formed shortly after the halo, possibly created or heated during an ancient merger event that puffed up the disk. The Milky Way is essentially a stellar family tree. At its base are the ancient ones, the halo stars and globular clusters that can be over 12 billion years old, tracing back to the galaxy's youth. Then come the thick disk stars, slightly younger. Then the majority of the thin disk stars like our Sun, younger still. And at the tips of the branches, constantly budding, are the new stars being born today. The galaxy's current star formation rate is a few solar masses per year, meaning on average, a few new stars, some massive, many small, spark into existence each year across the entire galaxy. In regions like the Carina Nebula or the Sagittarius Arm, one can witness these newborns emerging and lighting up their surroundings. Interestingly, there's a chemistry to this evolution. The Milky Way's stars have gradually changed the composition of the galaxy's gas. Early supernovae seeded space with iron and magnesium. Dying red giants puffed out carbon and nitrogen. Neutron star collisions, rare but dramatic, may have forged gold and platinum and flung them into space. Over billions of years, the galaxy's gas has become a richer chemical stew, enabling new types of objects, like planetary systems with solid planets. Astronomers sometimes call this process chemical evolution, and they track it by measuring the spectra of stars, reading the barcode of elements present. In doing so, they can identify stars that share a common origin or era. For example, one might find a group of stars spread through the halo that all have a particular scarcity of iron but excess oxygen, clues that they might have come from the same long-gone dwarf galaxy that had its own unique chemical history. Stellar evolution also drives cosmic timekeeping. The color and brightness of stars across the galaxy tell us the epochs of formation. The presence of massive blue stars indicates ongoing or recent star formation, since those don't live long. The presence of many red giants indicates an older population. In the Milky Way, we see both. The arms are lit with blue stars, the bulge with red giants. We are living in a galaxy that is still actively forming stars, though not as furiously as it once did in its youth. Perhaps our Milky Way in its past had starburst periods when it churned out stars at a much higher rate, maybe triggered by mergers. Now it's in a more quiescent middle age, creating stars steadily but more slowly. However, middle age does not mean inactivity. Right now, as you listen, somewhere in the Milky Way, a star is exploding in a supernova, ending its life. Somewhere else, a cool cloud is fragmenting, and the spark of a new star is catching fire. A sun-like star might be quietly swelling into a red giant and engulfing any close planets. A binary pair of stars might be exchanging mass in a delicate gravitational dance, one siphoning from the other, perhaps to eventually trigger a nova eruption. The galaxy is alive with stellar happenings at every moment, a grand fireworks show in extreme slow motion. Each star also carries within it the memory of the galaxy's evolution. By studying them, scientists piece together how the Milky Way grew. For instance, they found some stars in the halo moving backward relative to the general rotation, evidence of an ancient collision that brought in stars on different orbits. They found that the thick disk has distinct chemistry, suggesting a turbulent formation, possibly a massive merger about 10 billion years ago that heated the early thin disk. Thus, the stellar populations and their properties are like pages in a history book. We live among these stars, unaware in daily life of their grand narratives. But if you step back, you can see that the Milky Way's stellar population is a complex tapestry, with threads of different ages and origins woven together by gravity. Ultimately, stellar evolution in the Milky Way is a story of continuity and renewal. Stars are born from the ashes of their ancestors and return material to keep the cycle going. It's poignant to think that in the future, long after we're gone, the atoms that currently make up Earth and our bodies might one day be blown into space by the sun's distant red giant phase, becoming part of a nebula, perhaps to be incorporated into new stars or planets. We are a part of this cosmic recycling. Our galaxy is not a static collection of eternal lights. It is a dynamic, evolving ecosystem of stars. As we leave the stellar garden, marvel at its variety, the hot, young stars shining like blue-white fireworks, the stately middle-aged stars like our sun nurturing planets, the elderly red stars casting a gentle glow, the ghosts of stars, white dwarfs, neutron stars, black holes, remnants that whisper of lives that came before. The Milky Way contains all of these in vast numbers. It's a stellar society spanning all stages of existence. With an appreciation for the lives of stars, we proceed to consider the material that both creates and is created by those stars, the gas and dust that fill the spaces between stars, the substance from which new worlds emerge and into which old ones dissolve. Gas and dust. Between the stars of the Milky Way lies the interstellar medium, a diffuse mixture of gas and dust that is the bloodstream of the galaxy. Though the night sky might look like mostly empty space with isolated stars, in truth, the galaxy is filled with this very thin matter. Gas and dust weave silently through the Milky Way's disk, concentrating in some places and dispersing in others, fueling starbirth and absorbing starlight. This is the galactic ecology's raw material, the substance that makes new stars and planets possible. It is also the main obstacle to our view, painting dark brushstrokes across the glowing canvas of the Milky Way when seen in visible light. What is this gas? Mostly hydrogen, the simplest and most abundant element, with a seasoning of helium and traces of heavier elements. In some regions, it's hot and ionized, in others cool and molecular, spread thinly on average, just a few atoms per cubic centimeter in typical regions, far emptier than any vacuum we can create on Earth. It nonetheless adds up across the vast reaches of space. Gas constitutes a significant fraction of the galaxy's normal matter. If you could gather all the gas in the Milky Way, it would equal billions of suns in mass. And the dust? Tiny solid grains, submicroscopic, composed of elements like carbon, silicon, oxygen, iron, the ash of stars, forged in supernovae, or the winds of red giants. Each dust mote is perhaps like a fine soot or sand grain, often coated with ices or organic molecules in cold clouds. Dust might only make up 1% of the mass of the interstellar medium, but its impact is outsized. It is extremely effective at blocking and scattering light. It's the dust that creates those prominent dark rifts that cleave the Milky Way's band in the sky, giant dust clouds obscuring the stars behind them. To our eyes, those regions look like cosmic voids, but truly, they are filled with material, just not luminous, invisible light. In fact, those dark clouds often harbor the conditions for future star formation, hiding embryonic stars in their lightless embrace. Gas and dust often gather together. In the spiral arms, as density waves pass through, gas clouds get compressed. Picture vast clouds, tens of light years across, cold and quiet, primarily molecular hydrogen, with dust sprinkled in. These are the giant molecular clouds, the cradles of stars. One such cloud in the constellation Orion is visible to us as a faint, hazy patch, the Orion Nebula, where young stars are lighting up the gas. Other clouds are entirely dark, detectable only by the way they block background starlight or via radio emissions from molecules inside them, like carbon monoxide, which astronomers use as a tracer. These clouds can contain the mass of thousands or even hundreds of thousands of suns. Within them, dust shields the interior from harsh starlight, allowing molecules to form and temperatures to drop to just a few tens of degrees above absolute zero. In these frigid, dense pockets, gravity can overcome pressure and cause parts of the cloud to collapse, initiating star formation. Thus, gas and dust are the maternity wards of the galaxy. As new stars ignite inside a cloud, their radiation and stellar winds begin to disperse and sculpt the gas. They create glowing H2 regions, zones of ionized hydrogen that shine with a reddish-pink hue in photographs. These nebulae are essentially the cloud's announcement that stars have been born. The Trifid Nebula, the Lagoon Nebula, the Eagle Nebula, with its famous pillars of creation. These are all examples within our Milky Way of gas, lit up by newborn star clusters, captured in stunning detail by our telescopes. In these images, we often see towers and pillars of denser gas resisting the onslaught of radiation, sometimes harboring yet more protostars at their tips. The interplay of starlight and cloud creates beautiful structures, like cosmic sculpture parks carved by ultraviolet light. Eventually, the young star's energy blows away the remnants of the parent cloud, dispersing the gas and dust back into the general interstellar medium. There, the material may drift until another spiral arm or compression gathers it again. Not all gas is in cold clouds. There is also warm interstellar gas spread throughout the disk, partially ionized by ultraviolet starlight, creating a very tenuous plasma that fills much of the volume. There are hot bubbles too, cavities blown by supernova explosions where gas has been shock-heated to millions of degrees and is expanding outward. The galaxy's disk likely has a patchwork of these phases: cold, dense clouds, warm, diffuse gas, and hot, ionized bubbles. They coexist like different climates across the lands of the Milky Way. Gas and dust serve as a record of events. When we find certain heavy elements or isotopes in the gas, we know a supernova contributed them. When we detect complex organic molecules in a cold cloud, we realize chemistry is happening in space. Molecules like formaldehyde, alcohols, even simple sugars and amino acid precursors have been identified in interstellar clouds. It's astonishing. In the emptiness of space, tiny dust grains can catalyze the formation of complex molecules so that clouds many light years away hold some of the same chemical ingredients that on Earth lead to life. This interstellar chemistry is a rich field. One could say the galaxy has its own chemistry lab, continuously running experiments in the cold and dark, forging new molecules that one day might be incorporated into planets or even life forms. We owe a lot to dust. It facilitated the cooling of clouds to form stars, and later, in protoplanetary disks around new stars, dust grains clumped to form planetesimals and eventually planets. But dust also obscured our view. For centuries, it hid the true extent of the Milky Way. Early star counters like William Herschel in the 18th century tried to gauge the galaxy's size by counting stars in different directions,
not realizing that dense dust clouds blocked the light in some directions. This led to an underestimated size and a mistaken idea that the Sun might be near the center of the galaxy. Only later did astronomers like Harlow Shapley realize, by studying globular clusters, which lie outside the dust of the disk, that the center of the Milky Way was far away in Sagittarius, and that our galaxy was much larger than previously thought. The dust had fooled us by dimming distant stars. Today, we have overcome dust's veil by observing at different wavelengths. Infrared light can penetrate dust much more effectively, allowing telescopes like Spitzer and now the James Webb Space Telescope to peer into dusty regions and see stars being born. Radio waves from certain atoms or molecules, like the 21 centimeter line of neutral hydrogen or rotational lines of CO, allow us to map the gas distribution throughout the galaxy, dust or no dust. These techniques revealed the spiral arm structure by tracing the gas that makes them up, even when those arms lie on the far side of the galaxy, hidden behind intervening dust. In fact, one of the first maps of the Milky Way's spiral structure came from radio observations of hydrogen gas. The dust, which once hid our galaxy's structure like a veil, has had that veil lifted by modern astronomy. Gas also connects the Milky Way to its environment. The outer reaches of the galaxy's halo contain very diffuse gas clouds, some of which are left over from interactions with satellite galaxies. A famous example is the Magellanic Stream, a long ribbon of gas trailing behind the large and small Magellanic Clouds, two of our satellite galaxies, as they orbit the Milky Way. This stream, tens of degrees across the sky, is essentially those galaxies' gas being stripped and drawn toward our own. Eventually, that gas may rain down onto the Milky Way's disk, galactic rain, and fuel future star formation. There are also high-velocity clouds, mysterious giant blobs of gas moving quickly relative to the rest of the galaxy, possibly remnants of past encounters, or cold gas from intergalactic space captured by our halo's gravity. Within the disk, gas moves and flows. As the galaxy rotates, differential rotation can shear giant clouds, draw them into spiral patterns. When supernovae explode, they can send out shock waves that compress nearby gas, potentially triggering new star formation in surrounding clouds, a process akin to a chain reaction of starbirth. Alternatively, multiple supernovae can combine their shock power to punch holes in the disk and blow gas out into the halo, creating galactic fountains of hot gas that eventually cool and fall back. In this way, gas cycles not just in and out of stars, but also between disk and halo in a circulation often called the galactic fountain. The dust, for its part, sometimes shows us beautiful phenomena. In the densest clouds, dust is so opaque that optical light can't get through. But if there are bright stars nearby, dust can reflect their light, creating reflection nebula. Ethereal blue glows near young stars. Blue because dust scatters blue light more easily, similar to why our daytime sky is blue. We see this in the Pleiades star cluster. The hot young stars are surrounded by a blue sheen from dust reflecting their light. Dust also causes distant stars to redden. Since blue light is scattered out, more red makes it through, a clue to its presence. As we float conceptually through a spiral arm, we would pass through regions of dense gas and dust where stars are forming, then into clearer spaces where older stars roam, and perhaps past the bubbles of prior supernova. It would be like driving alternately through foggy patches and clear skies on a country road at night, sometimes seeing only nearby things, other times seeing far. In a poetic sense, gas and dust are the breath of the galaxy. They move, they flow, they condense and dissipate as the Milky Way lives and evolves. They are invisible to our unaided eyes, yet they make their presence known through the twinkle of starlight. Stars twinkle partly due to Earth's atmosphere, but interstellar gas can also cause scintillation or dimming over vast distances, and through the absorption of light, carving dark river-like shapes in the Milky Way's band in the sky that inspired so many myths. One such dark shape, visible from Earth's southern hemisphere, is the Coal Sack Nebula, a prominent dark cloud in the Crux constellation, which appears as a big hole in the Milky Way's starband. Australian Aboriginal peoples saw such dark clouds as significant shapes as well. Some saw an emu outlined in the darkness against the Milky Way. These cultural interpretations were early acknowledgements of interstellar dust's visual effect, long before science understood them as clouds of dust. Consider also that the interstellar medium whispers with electromagnetic radiation. The 21-centimeter radio whisper of neutral hydrogen permeates the galaxy. If you tune a radio telescope to that frequency, you can literally detect the diffuse hydrogen gas between the stars. It's a very faint signal, but it's everywhere, a kind of secret language that atoms are speaking across the galaxy. Using it, astronomers map spiral arms and measure rotation. As we appreciate gas and dust, we should also note the role of galactic magnetic fields. Though hard to imagine, our Milky Way has a magnetic field threading through its gas, a bit like the Earth has a field, though far weaker, on the order of microgauss. These magnetic lines influence the motion of charged particles and the alignment of dust grains. Sometimes we can detect the polarization of starlight caused by dust grains aligning with magnetic fields, giving us a glimpse of this invisible component. It's as if the galaxy has an unseen lattice that can gently steer particles, another layer of complexity in the interstellar medium. These fields might help channel cosmic rays, high-speed charged particles, through the galaxy and possibly affect star formation by providing pressure in gas clouds. In sum, gas and dust are the Milky Way's substance of creation and change. They form the clouds that birth stars, carry the products of stellar death, obscure and redden the light, and bridge the space between stars with a tenuous presence. They are, in a way, the memory of the galaxy's past and the womb of its future. Every star that will ever shine in the Milky Way will come from the gas and dust that float among the current stars, and every star that dies will return much of its substance to that reservoir. It's a cycle of cosmic reincarnation. Now, having explored the diffuse media that bind the stars, let us journey to the center of the Milky Way, a place both wondrous and forbidding, where the density of stars soars and an enigmatic darkness sits enthroned at the core. The galactic center. Toward the constellation of Sagittarius, hidden behind swathes of dust, lies the Milky Way's mysterious capital, the galactic center. This is the central hub of our galaxy, a place of extremes and secrets. If the Milky Way is a city of stars, then the galactic center is downtown, vibrant, crowded, and always bustling, yet also home to the darkest, most enigmatic figure in our galaxy's story, a supermassive black hole. Approaching the galactic center, in our mind's eye, since physically it's 26,000 light-years away, the first thing we'd notice is the sheer density of stars increasing. In the inner few hundred light-years, stars are packed like a glittering swarm. Within just 1 light-year of the center, it's estimated there are millions of stars. Compare that to our neighborhood around the sun, where the nearest star is over 4 light-years away. In the galactic center, stars can be only weeks of light travel apart from each other. The night sky from a planet in that region would be dazzling beyond imagination. Darkness scarcely exists, as you'd be surrounded by countless brilliant stars in every direction. Most of these central stars are older, redder stars, members of the bulge population. But intriguingly, intermingled among them are some blue stars, surprisingly young stars found very close to the black hole. How they got there is an active question in research. Possibly they formed from gas, funneled to the center, or maybe they were brought in as part of star clusters that migrated inward. Regardless, it means the galactic center is not just a graveyard of old stars. New life can spark, even in this hectic environment. Now, at the very core, at the precise center of the Milky Way's rotation,
resides Sagittarius A, pronounced Sagittarius A star, the supermassive black hole of about 4 million times the mass of our Sun. It's currently quiet, a sleeping giant, but it profoundly affects its neighborhood. Stars closest to it are whipping around at speeds up to a few % of the speed of light, caught in its intense gravitational grip. We know this because astronomers have observed these stars, the so-called S-stars, over decades, tracking their orbits using infrared telescopes that can see through the dust. One star, named S2, orbits the black hole on a highly elliptical path that takes it within just 17 light hours of the black hole, about 120 AU, only a few times farther than Neptune is from our Sun, at its closest. At that point, S2's speed is an astonishing 3% of light speed, 5,000 km/h. It completes one orbit every 16 years. Watching these stars swing around an unseen point showed conclusively that an extremely massive, compact object, a black hole, must lie at the center. This earned scientists like Andrea Ghez and Reinhard Genzel Nobel Prizes, as it provided some of the best evidence for the existence of supermassive black holes. Standing near the black hole, though one cannot truly stand there, one would witness bizarre effects. The gravitational field is so strong that light from stars behind it gets bent and distorted. Time itself runs a bit slower, closer to the black hole compared to farther away, a result of general relativity. Yet, Sagittarius A is relatively gentle as far as black holes go, because it's in a quiet phase, not actively devouring large amounts of matter right now. If it were active, we would see a bright beacon of high-energy radiation, X-rays, etc., and perhaps jets of particles shooting out from the poles, as seen in quasars. Instead, our black hole dines modestly. Occasional small gas clouds or asteroids might wander too close and get swallowed, producing flares. Indeed, astronomers have seen occasional X-ray and infrared flares from Sagittarius A, likely from small chunks of matter heating up just before disappearing across the event horizon, the point of no return of the black hole. The environment around the black hole is not empty. There's a swirling disk of gas and dust, though currently thin, known as an accretion flow. There are also clumps of matter like the intriguing object called G2, initially thought to be a gas cloud on a collision course with the black hole in 2014, but which survived the encounter and might conceal a star at its core. Additionally, the central region houses some unique astrophysical objects. Clusters of massive stars, the Arches and Quintuplet clusters, perhaps formed in starbursts a few million years ago, and many pulsars and X-ray binaries likely exist there, though they are hard to detect due to crowding and interstellar absorption. Moving out a bit, say within the inner few hundred light-years, what we call the central molecular zone, the gas density increases. There are massive molecular clouds swirling around the center, some arranged in a ring or torus about 2 to 5 light-years from the black hole, often called the circumnuclear disk. These clouds are subject to strong tidal forces and sometimes fall inward, feeding the black hole in dribs and drabs. The region also has unusually strong magnetic fields and cosmic ray activity. It's as if the vicinity of the galactic center is a different world compared to the quieter suburbs where we live. One of the most remarkable large-scale features tied to the galactic center are the Fermi bubbles. In 2010, scientists using the Fermi Gamma Ray Space Telescope discovered 2 enormous lobes of high-energy emission extending above and below the plane of the galaxy, centered on the core. Each bubble is about 25,000 light-years tall. They rise like twin balloons or mushroom clouds from either side of the nucleus. These bubbles shine in gamma rays and X-rays, indicating they are filled with extremely hot gas and cosmic ray particles. They likely attest to an energetic event in the Milky Way's center a few million years ago, perhaps a period when Sagittarius A devoured a batch of matter
and blew out a pair of jets, or a burst of star formation and supernovae in the core that drove a galactic wind. Today, the bubbles are fading, but still glowing, ghostly echoes of that past activity. If we had gamma-ray vision, the sky would have two huge ovoid shapes north and south, dwarfing the full moon. These show that while the galactic center is relatively calm now, it hasn't always been so. It has had its quasar-like moments or burps. From a human standpoint, if you could travel to the galactic center, ignoring lethal radiation and such, the sight would be awe-inspiring. Stars everywhere, a gentle reddish hue from myriad red giants, intense orbital dynamics, and at the very heart, a featureless dark void marking the black hole, perhaps detectable not by sight, but by the motion of stars, and by a faint glow of doomed matter around it. Actually, in 2022, the Event Horizon Telescope collaboration gave us our first image of Sagittarius A, a ring of radio emission around a dark center, the black hole's shadow, a bit like the famous photo of the M87 galaxy's black hole, but much smaller in angular size. It confirmed the presence of the expected event horizon silhouette, further proof of the behemoth lurking there. Culturally and historically, the galactic center was unknown to us until radio astronomy. In visible light, that direction is obscured by thick dust clouds, like the Great Rift. We only realized something special lay there when in the 1950s, strong radio emissions, Sagittarius A region, were detected. Over time, multi-wavelength observations peeled away the layers of obscuration. Now we know Sagittarius A not as just a radio source, but as a black hole. If Earth's night sky were not obscured by dust towards Sagittarius, who knows? Perhaps ancient astronomers would have built temples or stories around a bright object there. But instead, it was hidden, maintaining its mystery until modern times. The galactic center is also rich in molecules. The clouds in this zone have produced some of the most complex molecules detected in space, likely due to the higher density and interesting energy sources. For example, molecules like acetone, methanol, even ethyl formate, a molecule that smells like rum, interestingly, have been found in Sagittarius B2, a giant molecular cloud near the center. It's a chemist's treasure trove. It's fascinating to think that while we orbit calmly far away, the center is such a frenetic place, but its influence reaches us. The mass of the central black hole is negligible for the galaxy's overall gravity. The dark matter and stars dominate on large scales. But in aggregate, the central mass concentration anchors the rotation and influences the bar structure that extends across the inner galaxy, which in turn helps shape the spiral arms. It's all connected. At times, I picture the Milky Way's center as a kind of cosmic hearth, a fireplace at the center of a great hall. It may burn low or fiercely, but it's the focus around which the structure of the house is arranged. Right now, our hearth is glowing quietly, but who knows in a few million years or in the past? It might have flared, sending sparks, radiation, winds across the galaxy's inner regions. So as we think of the galactic center, we think of paradox. It is both the brightest concentration of stars and home to the darkest of objects. It's a place where time and space are warped by extreme gravity, yet from which our galaxy's spiral structure gracefully unfolds outward. It is central and crucial, yet largely hidden from our direct view. To feel it, we must rely on instruments and imagination. Let's pause a moment and imagine ourselves floating a few light years from Sagittarius A, shielded safely, looking outward. The sky is ablaze with the glow of 10 million stars. Perhaps we see the spiral arms from the inside, radiant streams extending outward. Above and below, beyond the disk, faint glows hint at the Fermi bubbles. The black hole behind us is invisible, save for the swirl of hot gas around it, making a sort of dim halo. We feel the space-time vibrating with activity, stars slingshotting by, X-ray flashes from small matter falling in, the hum of dense star clusters. It's both serene in its grandeur and terrifying in its intensity. In the silence of space, this chaos is oddly mute, but one can sense the energies at play. Having dared to visit the heart of the Milky Way, let us journey back outward a bit to consider something the galactic center helped reveal: the rotation curve of our galaxy and what that means, bridging back to our earlier thoughts on the invisible architecture. The rotation curve. One of the most illuminating ways to understand a galaxy is to study how it rotates. Imagine watching the Milky Way spin over time, sped up enormously, of course. How do the stars and gas move as a function of distance from the center? The graph of orbital speed versus radius is called the rotation curve. For the Milky Way, as with many other galaxies, the rotation curve holds a surprising story that forever changed our understanding of the cosmos. In a simple world, you might expect the inner parts of the galaxy to rotate fast and the outer parts to rotate slower, much like planets in the solar system, where Mercury zips around fast and distant Neptune moves more slowly. If most of the mass were concentrated in the center, like the Sun in our solar system, that's exactly what you'd see. Speeds would drop off with distance. However, when astronomers measured the motion of gas and stars at various radii in the Milky Way, they found something astonishing. Beyond a certain point, the rotation speeds did not drop off. They stayed roughly constant or flat, and even out to large radii remained high. In the inner region, inside roughly a few thousand light years, speeds increase with radius as one moves out from the central bulge. This is normal, because initially, you're still adding more enclosed mass as you go outward, so gravity grows. But beyond the inner bulge disk, instead of peaking and then declining, the curve plateaued. Stars and gas far from the core, tens of thousands of light years out, were orbiting at roughly 200 to 240 kilometers, nearly as fast as those much closer in. This flat rotation curve was one of the key pieces of evidence that led to the concept of dark matter, which we discussed in the invisible architecture. It told us that the mass of the Milky Way keeps increasing with distance far beyond the visible disk. There must be a lot of unseen mass out there providing the gravitational pull to keep those outer stars moving fast without flying away. Without that extra gravity, the outer stars and gas clouds, moving as fast as they do, would escape the galaxy's grip. The rotation curve basically mapped out the presence of the dark matter halo. As you go out, you keep encountering more mass that's not shining. However, even with this general understanding, scientists continue to refine the Milky Way's rotation curve with better data. It's not a perfectly flat line. It has subtle bumps and wiggles. For instance, around the Sun's orbit, 27,000 pounds-li, the speed is around 220 kilometers. Further out, it might gently rise or fall by small amounts. Recent precise measurements from Gaia and other surveys indicated the curve might even decline slightly in the far outer disk, suggesting maybe less dark matter in the outskirts than some models predicted, though the data are tricky. Still, broadly, it remains far higher at large radii than a visible matter-only galaxy would allow. One can think of the rotation curve as a kind of diagnostic of the galaxy's mass distribution. In the Milky Way, it tells us that the luminous parts, stars, gas, are only the tip of the iceberg of mass. The dark halo's distribution is such that even at distances where the starlight fades, mass is still accumulating. Historically, measuring the Milky Way's rotation curve had challenges because we're inside the disk. Astronomers used a clever method, observing the 21 centimeter radio emissions of hydrogen gas in different directions. In certain directions along the inner galaxy, they could measure Doppler shifts that indicated how fast gas was orbiting. By mapping the velocities as a function of galactic longitude and using geometry, they inferred the rotation speeds at different radii. External galaxies provided additional confidence. Vera Rubin's pioneering work in the 1970s on spiral galaxies showed flat rotation curves were common, not just an oddity of the Milky Way. The rotation curve is often plotted with orbital speed on the vertical axis and distance from center on the horizontal. For the Milky Way, it rises from 0 at the very center, though motions there are more random due to the bulge, peaks around maybe 200 to 240 km in the inner disk, and then stays around that value out to as far as we can measure, maybe 60,000 light-years or more. If the galaxy's mass ended around the visible edge, half 50,000 Panspermie radius, the curve would start dropping, but it doesn't significantly, indicating the halo extends much further. Think of a carousel again, but imagine invisible weights are hidden under the floor, extending way out beyond the visible platform. The horses near the edge keep going fast because those hidden weights provide the gravitational pull. There's also something poetic here. The stars in the Milky Way are essentially flying in enormous circles, guided by gravity's hand. We don't feel this motion sitting here on Earth, but it's real and enormous in scale. Each star's orbit is a balance. Its motion is trying to fling it away, but gravity pulls it in. At the radius of the Sun, that balance has us moving at roughly 500,000 miles per hour around the center. At the edge of the disk, a star might still be moving at 400,000 km/s. The galaxy's rotation is the reason the Milky Way has maintained a disk shape. If it rotated much slower, gravity would collapse more material inward. If it were faster, perhaps the outer parts would break away. Rotation also ties intimately with the spiral structure. The arms are not material arms that rotate like a solid object. They are patterns through which stars and gas move. The differential rotation, inner parts rotating faster in terms of orbital period than outer parts, means any material arm would wind up tighter and tighter. So the prevailing idea is that spiral arms are a kind of density wave that rotates at its own pattern speed, and stars enter and leave it, like cars moving through a traffic jam region. The rotation curve plays a role in where these pattern resonances occur. It's amazing that from the simple question, how do stars move in the galaxy, we unveiled something as profound as dark matter. The rotation curve is like the galaxy's heartbeat chart. For humans, a heart ECG can indicate health or problems. For the galaxy, the rotation curve indicates a hidden vital component. Let's reflect a moment on what it would feel like if we could sense this rotation personally. Right now, sitting or standing, you might feel at rest, yet you are on a planet spinning on its axis, orbiting the Sun, and also careening around the galactic center. The motion around the galaxy is by far the fastest of these at any given moment, since 220 km dwarfs Earth's orbital, 30 km or rotation, still 0.5 km at equator. So we are all passengers on a starship called the Solar System, cruising through the Milky Way at tremendous speed. The stars we see near us share roughly the same orbital motion. They're our fellow travelers. More distant stars, if you track them long enough, show up with different velocities due to perspective and their position. Gaia's measurements of star motions let us see the kinematics in exquisite detail. How some stars stream together in groups, perhaps remnants of disrupted clusters or past mergers. How the disk might have subtle waves or corrugations, possibly from the influence of satellite galaxies, like the Sagittarius Dwarf or LMC. The rotation curve, being flat, implies the presence of that dark halo we spoke of, which itself is a major character in our story. Without dark matter's gravitational support, the Milky Way might not have formed as it did, and the rotation would be quite different. Some alternate theories have been proposed, like modified gravity theories, to explain flat rotation without dark matter, but none have matched all evidence as well as the dark matter halo model for our galaxy and others. From a narrative perspective, the rotation curve is like reading the galaxy's diary in a language of motion. It told us that the Milky Way has more to it than meets the eye, an insight somewhat akin to reading someone's calm outward expression, but sensing an underlying strong heartbeat. It's the clue that led us down the path of acknowledging the invisible architecture in quantitative detail. As we continue outward or onward in our journey,
The rotation curve concept will segue nicely into discussing the dark matter halo specifically, since it's responsible for that shape of the curve. We have essentially set the stage. The galaxy rotates in such a way that reveals the dark matter. Now we'll explore that halo in more depth, albeit in a poetic tone, since dark matter is inherently mysterious.
So, with stars swirling around us in a gravitational dance and speeds that defy the luminous mass, we prepare to meet the dark halo face to face, or rather, face to something we cannot see, but know is there by its embrace. Dark matter halo. Enveloping the Milky Way like a cocoon is the dark matter halo, a vast and enigmatic component that extends well beyond the visible galaxy. We've already felt its gravitational influence in the flat rotation curve and the invisible architecture. Now let's visualize this halo and contemplate its nature and significance, as if meeting the ghost in our galactic home. Imagine a sphere centered on the Milky Way, perhaps as large as 1,000,000 light-years across, nearly half the distance to the Andromeda galaxy. Within this sphere, sprinkled very lightly, are particles of dark matter, something we do not yet understand fully, be it an exotic particle or something stranger, but which has mass and thus gravity. These dark matter particles neither emit nor absorb light. They pass through ordinary matter, almost as if it wasn't there, interacting mainly via gravity. They are elusive. Billions might be passing through you right now without a trace. Yet, their cumulative effect around the galaxy is immense. They account for about 90% of the Milky Way's total mass.
The dark matter halo likely formed early, before the galaxy's stars were born. In the young universe, slight density variations caused some regions to collapse into clumps dominated by dark matter. These were the seeds of galaxies. One of those seeds became the halo of the Milky Way, pulling in gas which then formed stars and the disk within. Over time, smaller halos merged, assembling into the larger halo we have now, dragging their luminous contents, stars, gas, with them. Even today, the halo might have substructure, clumps or subhalos of dark matter, perhaps hosting small satellite galaxies or just invisible on their own. What is the shape of our dark halo? We often imagine it spherical, but it could be a slightly squashed sphere, triaxial, or oblate. Studies of stellar streams, remnants of torn-apart dwarf galaxies, serve as tracers, like throwing paint on an invisible object to see its outline. These studies suggest the halo might be a bit elongated or lopsided, especially given a big lump like the Large Magellanic Cloud may even distort it a bit. But roughly, it's a huge roundish cloud of mass around the Milky Way. In that halo, aside from dark matter, there's a tiny population of visible things, the halo stars and globular clusters we discussed, and the satellite galaxies orbiting within it. They are like fireflies around an elephant, bright but insignificant in mass compared to the dark matter bulk. If you could view the Milky Way from afar in the dark matter spectrum, whatever that might be, you'd probably see a smooth glow, if dark matter glowed, about 10 times the diameter of the visible spiral, maybe tapering off gradually at the edges, with slight ripples where subhalos might reside. The visible galaxy would lie at the center as a bright jewel in a glass paperweight. This halo is the gravitational cradle of our galaxy. It keeps everything bound together. When our galaxy engages in cosmic interactions, it is the dark matter halo that largely dictates the outcome because it's the dominant mass. For instance, if the Milky Way passes near another galaxy, it's the halos that feel each other first, tugging gravitationally like invisible giants meeting before the visible galaxies ever touch. Dark matter's presence also shields and shepherds the galaxy's content. It provides an additional gravitational well, such that even as the galaxy rotates rapidly, the stars remain secure in orbit. Without the halo, a fast-rotating disk might fly apart. The halo's gravity holds the disk intact, much like an egg's invisible gravitational field might hold a spinning yolk in place. if one can imagine such a thing. What is especially intriguing is that we know dark matter exists through effects like these, but we don't know what it is. It's one of the greatest scientific mysteries of our time. It could be a type of particle left over from the Big Bang that interacts only via gravity and perhaps the weak nuclear force. Many experiments on Earth are trying to directly detect a dark matter particle in underground detectors, so far without confirmed success. It could even be something more exotic, primordial black holes, or something not predicted yet. But in the grand narrative, in the Milky Way's tale, dark matter is a silent character who never speaks, never reveals its face, yet whose actions shape everything.
The halo does interact gravitationally with visible matter in ways beyond just holding it. It likely plays a role in how material flows into the galaxy. For instance, fresh gas from intergalactic space might be attracted by the halo's gravity, then slowed or shock heated upon entry. It may accumulate in the halo as hot gas. Some theories say there's a hot circumgalactic medium, a very low density, million-degree gas pervading the halo, detected via X-ray and UV absorption lines. That gas can slowly cool and rain onto the disk, fueling new star formation. So the halo could be seen as the galaxy's reservoir, catching incoming material in a gravitational net. The halo also can capture or destroy other small halos. When a dwarf galaxy ventures close, if the tidal forces from the Milky Way's halo exceed the dwarf's self-gravity, the dwarf gets torn apart. Its stars become streams. Its dark matter likely just assimilates into the Milky Way's halo. Over cosmic time, the halo has probably grown by eating many smaller ones, an unseen feast leaving behind star stream crumbs as the only visible evidence. It's mind-bending to consider that most of the Milky Way's mass lies in this unseen halo. To draw a metaphor, imagine meeting a person and discovering that 9/10 of their body is invisible, and you only see an arm, part of a face, and a foot perhaps. You'd realize you really don't know the full person at all. That's our situation with the galaxy. We see its stars and nebulae, the parts sticking out, but the bulk is hidden. And that is true for all galaxies, not just ours, hinting at something fundamental about the cosmos. For our narration, let's personalize the halo a bit. Think of it as a gentle giant surrounding the bright hubbub of stars. It's mostly quiet, interacting by gravity's pull. It doesn't shimmer or shine, but it has enormous influence. If the disk of the Milky Way is like the visible dance of a music box ballerina, the halo is the unseen mechanism that provides the structure and momentum for the dance. There's also a sense of melancholy with dark matter. It's so important, yet it doesn't partake in the flashy parts of cosmic evolution. No light, no chemistry, no forming of planets. As far as we know, dark matter cannot clump to small scales because it doesn't radiate energy, so it can't cool and collapse to form things like stars or planets. It stays in a large, diffuse halo. It's like a scaffold that builds a cathedral, but once the cathedral, stars, planets, is built, you take away the scaffold's visible role. Yet the scaffold was necessary. We might wonder, do dark matter particles pass through us? Yes, if they exist as particles. Earth is moving through the galaxy's halo, so presumably a wind of dark matter flows through at hundreds of km/s. They rarely, if ever, hit our atoms in a noticeable way, but experiments are trying to see a faint tap of a dark matter particle hitting a detector nucleus.
From a philosophical standpoint, the dark matter halo reminds us that much of reality might be hidden from direct view. In the Milky Way, what you see is not all there is. One must infer, deduce, and feel the effects of the unseen. In life, too, sometimes what's important is not immediately visible. It's a nice parallel. Now, another feature of having a dark matter halo is that it extends the influence of the Milky Way far out. There's no clear edge to the galaxy because of the halo. It gradually peters out. This makes the concept of where the Milky Way ends
fuzzy. Some define the edge where the escape velocity equals the rotational velocity, etc. But thanks to the halo, one could say our Milky Way has a radius on the order of 300,000 light-years or more, where the density of dark matter merges into the general background of space. The nearest big galaxy, Andromeda, has its own halo, and interestingly, these halos might already be touching or overlapping in the space between Milky Way and Andromeda, like two giant soap bubbles gently contacting. If so, then in some sense our local group, the group of galaxies including Milky Way, Andromeda, and some dwarfs, is one connected structure through the dark matter distribution. It's a lovely concept that even before the galaxies themselves collide, which they will in billions of years, their dark halos have met. In closing our consideration of the dark halo, let's envision drifting outwards from the bright disk into the realm of darkness. As the starlight fades behind us, we plunge into an almost empty vastness. But we're not alone. The gravitational pull is still with us, indicating mass all around like a subtle tension in space. Occasionally we might pass a lone globular cluster or a small satellite galaxy, little islands of light in the dark sea. But mostly, it's quiet and dark. If we could see the dark matter, maybe it would look like a faint mist or swirl around us. Perhaps it's clumpy. Maybe we pass through an invisible cloud that is a subhalo. We wouldn't know, except perhaps by a slight tug. The main Milky Way disk now is a small shining disk far behind, like a distant lighthouse. Yet the domain of our galaxy extends much farther, here in this dark realm. We realize that as we leave the visible behind, the Milky Way's influence has not ended. It extends its gravity out here in the silence. And interestingly, out here, we might find things like star streams and signs of galactic cannibalism, evidence of how the Milky Way grew. So now, let's follow one of those streams of stars, a tenuous bridge of lights crossing the dark halo, which tells the tale of galactic cannibalism, the ongoing process by which our galaxy has consumed others. Star streams and galactic cannibalism. In the Milky Way's halo, if you look closely, with the powerful eyes of missions like Gaia, you'll find stars arranged in long, arcing filaments, as if drawn out into lines by a cosmic comb. These are stellar streams, the remnants of small galaxies or star clusters that ventured too close to the Milky Way and were torn apart. They are the ghostly footprints of past galactic meals, evidence of what we call galactic cannibalism, the process by which our large galaxy grows by devouring smaller ones. Picture a smaller dwarf galaxy, perhaps millions or a billion stars, bound loosely together, orbiting the Milky Way. Over time, gravitational tidal forces stretch it. Stars from the dwarf begin to drift out, forming a stream, trailing and sometimes leading the core of the dwarf, like taffy being pulled apart. Eventually, the dwarf structure dissolves, leaving behind a stream of stars orbiting the Milky Way along what used to be the dwarf's path. These streams can wrap around the galaxy in huge loops. They're faint, but with precise measurements of star positions and motions, we can detect them as overdensities of similarly moving stars. One famous example, the Sagittarius stream, from the Sagittarius dwarf spheroidal galaxy, which has been in the process of merging with the Milky Way for billions of years. The core of this dwarf is still present, a dim, fuzzy galaxy on the opposite side of the galaxy from us, toward the constellation Sagittarius, hence the name. But it's being dismantled. Wraps of its stars have spread in a polar orbit around us. Indeed, part of that stream passes relatively near the Sun's position, though still tens of thousands of light years away. It forms a huge structure encircling the galactic halo. Imagine a gossamer ribbon of stars, too faint to see without telescopes, looping over the top of the Milky Way and around beneath. That's the Sagittarius stream. Another, the GD1 stream, thought to be from a globular cluster that was torn apart. Or the Palomar 5 stream, another shredded cluster leaving a thin stream behind. There are others like Orphan Chenab stream, poetically named because the progenitor is gone, an orphan, and the Helmi streams, discovered by an astronomer, Amina Helmi, which are remnants of a dwarf galaxy that merged early on. And then, one of the most significant events in the Milky Way's history has been deduced by studying the halo star's motions and chemistry, a collision about 8 to 11 billion years ago with a dwarf galaxy often called Gaia Enceladus, or the Gaia sausage. This oddly nicknamed object was a fairly large dwarf galaxy that smashed into the early Milky Way. Many of the halo stars and the halo's inner portions have orbits and compositions indicating they came from this event. The name sausage comes from a pattern in velocity space that looks like a sausage shape when plotted, identified in Gaia data. This merger is believed to have puffed up the Milky Way's thick disk and given it a lot of its halo. In a sense, we are partly a chimera. Our galaxy is partly built from the remains of that galaxy. After the collision, the stars of Gaia Enceladus were strewn into radial orbits, going out and back in, which is why in velocity space they have high radial motions but not much rotation, giving that sausage signature. That event likely also caused a burst of star formation and altered the structure of our young Milky Way. Galactic cannibalism may sound violent, and indeed on a cosmic scale, it is a sort of violence. But remember, stars are so far apart that when two galaxies merge, individual stars almost never collide. Rather, the system's gravitational fields merge. The smaller galaxies' stars simply find themselves gradually reassigned to orbit in the gravitational potential of the bigger galaxy, rather than their original small one. The violence is in the gravitational forces that rip the structure apart, and any gas in those galaxies can get compressed and create flashes of new stars, starbursts, or feed the central black hole, etc. Over time, the smaller galaxy is fully digested, its stars now just part of the halo or disk of the Milky Way, its distinct identity gone. Our Milky Way has probably consumed dozens of smaller galaxies over its lifetime. Some were long ago. Their stars are thoroughly mixed, and we only find hints by finding stars with unusual chemistry or orbits. Others are ongoing, Sagittarius, or recent, like Gaia Enceladus, 10 billion years is recent in a 13 billion year life. This process is common in the universe. Big galaxies like ours grew by hierarchical merging, assembling from smaller pieces. Even the Large Magellanic Cloud, LMC, that orbits us now is destined for this fate. The LMC and its smaller companion, the SMC, Small Magellanic Cloud, are falling toward the Milky Way. Within a few billion years, they might merge into us. Some models say the LMC will fall in sooner than Andromeda's arrival. When that happens, it will induce new star formation, perhaps create new streams, and add its stars, and even its own central black hole. The LMC likely has an intermediate mass black hole, which may merge with our central black hole eventually. This cannibalistic side of the Milky Way is a reminder that galaxies are not static islands. They are dynamic and continually evolving. For smaller galaxies in our vicinity, the Milky Way's gravity is a force of destiny. Over time, the Milky Way will incorporate many of them. It's almost like the mythology of Cronus devouring his children, except the Milky Way devours smaller siblings. But it's not malicious, it's just gravity doing its inexorable work. The stellar streams left behind have a serene beauty to them. I like to think of them as cosmic rivers in the galactic halo, or perhaps the fossil rivers of what once were independent galaxies. They also serve as signposts. For instance, the way a stream's path bends can tell us about the shape of the dark matter halo. The stream is essentially a test particle feeling the gravitational field. One day, maybe we'll map dozens of streams and thereby map the dark matter distribution precisely. Also, some globular clusters might be immigrants from swallowed galaxies. Some clusters have different properties that suggest they originally lived in a dwarf galaxy that got merged. and the cluster got adopted by the Milky Way. From our vantage in the solar system, these events are subtle. The night sky doesn't obviously show a stellar stream to our naked eyes, except maybe one can argue that the Milky Way's own band had to be recognized as our galaxy, not a stream through it. That was another story from Shapley versus Curtis. But through telescopes, we can detect certain patterns. For example, the Sagittarius dwarf galaxy can actually be imaged as a faint concentration of stars, only discernible with telescopic surveys. And if you plot the positions of certain types of stars, like RR Lyrae variables or blue horizontal branch stars, which often reside in old populations, at large distances, you can see overdense bands corresponding to known streams. Galactic cannibalism will continue into the future. Eventually, the Milky Way itself will be devoured, or rather, merged, when we collide with Andromeda. But by then, in that merged entity, all the smaller galaxies we had left, maybe the Triangulum galaxy, M33 possibly, plus any dwarfs, will fall in as well to form one big elliptical or diffuse galaxy. Our local group will become one large Milky Andromeda hybrid, sometimes playfully called Milkomeda. The notion of cannibalism is stark, but there's a constructive side. Each merger brings new material. The mixture of gas can spur star formation. New stars, clusters, maybe even new nebulae and structures are born from the union. It is a mode of cosmic renewal. The halo's very existence as a blended repository of many origins gives the Milky Way a kind of genealogical richness. If you take one halo star, measure its chemistry, you might find, oh, it has very low magnesium relative to iron that matches stars from this specific dwarf galaxy's pattern. That star might truly be from a galaxy consumed 10 billion years ago. It's like an immigrant star now living in the Milky Way, but carrying the accent of its birthplace in its elemental makeup. In that sense, the Milky Way is a melting pot of stars from different lineages. Much like modern cities contain people from diverse origins, the Milky Way's halo contains stars from a variety of prior smaller galaxies. We can stand under the night and not know that a star twinkling above might have originated outside our galaxy entirely. But the science tells us that's likely the case for many halo stars. Let us imagine following a stream. We drift along a line of stars in the halo. They stretch before us, hundreds of light years wide, but tens of thousands of light years long, gently curved around the galaxy. They are relatively sparse compared to the disk. If you were in the middle of a stream, you might still have to travel many light years to go from one star to the next. But relative to the emptiness around, it's a marked overdensity, like a barely visible road in a desert. We follow it inward. It leads us to a dwindling remnant of a once proud dwarf galaxy, perhaps a tightly bound cluster of stars that was its core. We follow it outward. It fades into the background of the halo. Over time, even the stream will diffuse further, as stars in it gradually spread out due to slight differences in their orbits. Streams are transient over billions of years, eventually becoming part of the general smooth halo background. The concept of galactic cannibalism invites philosophical reflection. Nature seems harsh on these scales. Big galaxies eat little ones. But it's also just the flow of gravity, not driven by intention. And from the ashes of that process arises something new, a larger galaxy, possibly capable of forming new stars and even new planetary systems that would not have existed otherwise. So there's destruction, but also creation in a new form. Now, beyond streams, we should note that not all satellites are completely destroyed yet. Some still exist around us. The satellites are basically meal preparation in a sense. We've touched on that, but it's worth giving them their spotlight next, before they too eventually face either merging or just orbiting ad infinitum. So let's now visit those satellite galaxies. The companions currently in the Milky Way's retinue, orbiting like the moons of a planet, though on a much bigger scale, some destined to become the next star streams in the far future. Satellite galaxies.
The Milky Way is not alone in the cosmic ocean. It is accompanied by a swarm of smaller satellite galaxies bound in its gravitational embrace. These satellites are galaxies in their own right, but much smaller and fainter than the Milky Way, and they orbit around our galaxy like tiny fish around a great whale. They provide a sense of context. Our Milky Way, large as it is part of a local community of galaxies. The two most famous satellites are visible to the naked eye from the southern hemisphere: the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These appear as hazy, cloud-like patches in the deep southern sky, so much so that early explorers thought them to be clouds, hence the name. In reality, they are dwarf galaxies. The LMC is a barred spiral or irregular galaxy about 163,000 light-years away, roughly 1/10 the mass of the Milky Way, containing on the order of 30 billion stars. The SMC is about 200,000 light-years distant, with perhaps a few billion stars. These two are likely a bound pair and have been orbiting the Milky Way together. They have had a huge impact on our galaxy. Their gravity may be tugging on our disk, possibly causing asymmetries and warps, and gas outflows from them, the Magellanic Stream we mentioned, are feeding our halo with fresh material. The Magellanic Clouds are rich in gas and still forming stars. They have vibrant nebulae like the Tarantula Nebula in the LMC, which is one of the most active star-forming regions in the local group, a cauldron of massive stars and supernova remnants. If we look at them with telescopes, we see a flurry of star clusters and nebulae. They are like miniature versions of galaxies that remind us of how the Milky Way might have looked when it was smaller, or how galaxies across the cosmos often appear. Beyond the clouds, the Milky Way has dozens of dwarf spheroidal galaxies as satellites. These are faint, fuzzy objects scattered around the halo, many discovered only in recent decades with deep imaging surveys. They have poetic names often after the constellations they're found in: Draco, Ursa Minor, Sculptor, Fornax, Carina, Sextans, Sagittarius, which we already discussed being cannibalized, and many ultra-faint dwarfs like Willman 1, Segway 1, Bootes 1, etc. These dwarfs typically have only a few million to a few tens of millions of stars. Some of the ultrafaints just thousands of stars. They are heavily dominated by dark matter, interestingly, meaning the visible stars are just a tiny fraction of their mass. They're like little dark matter mini halos with a sprinkle of stars. Because of this, they are dynamically very stable, lots of dark matter to hold them. They have very old stellar populations, indicating they stopped forming stars long ago. Perhaps their gas was stripped early by the Milky Way, or they used it up quickly. They appear as little smudges in telescopes, often requiring long exposures to discern from foreground stars. One might ask, how many satellites does the Milky Way have? The number keeps growing as we find fainter ones. Currently, known ones are on the order of 50 to 60. The bright ones can be counted on fingers: Magellanic Clouds, Sagittarius, and maybe a dozen classic dwarfs discovered mid-20th century. But newer digital sky surveys are revealing extremely faint ones that push the limits of detection. We suspect there might be even more, lurking in parts of the sky not fully surveyed or hidden by the Milky Way's disk, or simply too faint to pick out easily. These satellites orbit at various distances. Some, like the Magellanic Clouds, are relatively close, under 200 Li. Others, like Leo 1, are quite far, over 800 Li. They orbit in what seems like somewhat random orientations, though there's some research suggesting maybe some align in a kind of plane, or come in groups possibly associated with cosmic filament structures. It's still debated if there's a satellite plane, or if that's a chance arrangement. The gravitational dance between the Milky Way and its satellites can have effects. The LMC, being the largest, is thought to be on its first approach possibly. Some studies propose the LMC might have only recently been captured. If so, the halo of the Milky Way might be moving a bit in response. The center of mass of the Milky Way LMC system might shift, causing our galaxy to slightly wobble. Some recent papers discuss the idea that ignoring the LMC's influence could bias measurements of the Milky Way's mass.
Each satellite galaxy is like a chapter in the Milky Way's story. Some might be future meals. Some might just remain satellites indefinitely. For example, ultra-faint dwarfs might not easily merge because they're so small and diffuse. They might just get gradually stripped away over time. Others, like Sagittarius, are clearly on the menu. The Magellanic Clouds might merge soon, in cosmic terms, say within 2 billion years possibly for LMC.
Satellites are also interesting as laboratories. Being simpler and smaller, they help us test models of dark matter on small scales and star formation in tiny potentials. They show that not all galaxies look like grand spirals. The majority in the universe are actually these small dwarfs. Poetically, I think of the satellites as a retinue of companions or children of the Milky Way. If the Milky Way is a great tree, these are the saplings around its base, some of which will eventually be reabsorbed into the soil to feed the great tree. Others may be transplanted by cosmic currents. They remind us of scale. What's small and faint compared to the Milky Way might itself hold thousands or millions of stars, and likely countless planets.
Yes, consider that too. Each dwarf galaxy, even if it has 1 million stars, likely has planets. Could there be life in a satellite galaxy, gazing at the Milky Way as a giant spiral in their sky? Perhaps a planet in the LMC has a view of our galaxy somewhat like we see Andromeda, a big object in their night sky. Quite a perspective. Culturally, the Magellanic Clouds were known to peoples of the southern hemisphere for millennia. European explorers in the Age of Sail took note of them during voyages, hence named after Magellan by Pigafetta, though many indigenous cultures had their own names. They have always been a curiosity. What are these patches? Only in the 20th century did we measure their distance. Harlow Shapley did important early work on the SMC's distance using variable stars, and realized they are separate galaxies outside our own. The awareness that the Milky Way had companions was part of the bigger picture. Not only is the Milky Way not the whole universe, as the great debate settled by recognizing other galaxies, but even our galaxy itself has a system of smaller galaxies around it, a sort of microcosm of the macrocosm. We have our own mini-local group around just us. One of the nearest dwarf satellites is the Canis Major overdensity, discovered around 2003, which might be the core of a dwarf galaxy in process of merging, only 25,000 Poundsley from the center, which is inside the disk's radius. It's controversial, but there is evidence of a cluster of stars near Canis Major direction that could be a merging dwarf. If true, it's basically getting eaten now, and might be responsible for some rings of stars in the disk, like the Monoceros ring. This shows how the line between satellite galaxy and galactic structure blurs when cannibalism is happening. In the cosmic future, after Andromeda merges and everything settles, likely many of these current satellites will either be part of the big elliptical or flung out. Right now, they are like little birds around a big one, but when big birds come together, Milky Way plus Andromeda, the flock gets reconfigured. To visualize satellites, think of a three-dimensional model. At the center, the Milky Way disk. Dotted around at various distances, small fuzzy blobs. Some closer in, Sagittarius trailing streamers. Some mid-range, LMC, SMC, Fornax, etc. Some far out on the fringe, Leo Were, near edge of our halo. They each orbit at tens to a couple hundred kilometers speeds in some orbit. Over billions of years, we'd see them swarming, occasionally spiraling in. Interestingly, satellites can also survive if in stable orbits, especially if they're in a distant orbit and not a lot of dynamical friction, which slows down orbits of big objects moving through halos. Ultrafaints might hang around indefinitely if not disturbed. The LMC, being relatively massive, will probably spiral in faster due to dynamical friction. It's like how in a fluid, a big object slows quicker than a small one due to drag. We should also mention satellites like Ursa Minor Dwarf,
Draco dwarf, faint but historically known, discovered in 1950s from photographic plates. And Fornax dwarf has some globular clusters of its own, a dwarf galaxy that has its own satellites, mini globular clusters, adding layers. So, the Milky Way is a system with subsystems. It's hierarchical. As part of our journey, perhaps now we stand metaphorically at the edge of the Milky Way's domain, looking at a sky not dominated by a single galaxy, but by many small companions scattered around. Perhaps from a vantage point in the halo, we could see the Magellanic Clouds off to one side, maybe glimpses of other dwarfs as faint smudges if our eyes could integrate light long enough. It would emphasize that the Milky Way is the central hub of a small cluster of galaxies. With satellites in mind, one naturally wonders, at the core of each satellite, is there something like a black hole or remnant? Possibly the LMC likely has one, others might not. Dwarfs might have only intermediate mass or none. But we know the Milky Way has one for sure at the center. And not just the central black hole. There are stellar mass black holes and other remnants peppered throughout. Let's now contemplate those black holes and remnants that permeate the galaxy after millions of star lives. The skeletons in the galactic closet, so to speak. Black holes and remnants. Throughout the Milky Way, hidden in the darkness, lie the corpses of stars, white dwarfs, neutron stars, and black holes, the remnants left when stars die. These objects are the end states of stellar evolution, and they are as much a part of the galaxy as the shining stars, though they emit little or no light of their own, apart from some exotic behaviors. In a sense, they are the galactic ancestors, the silent remnants of previous generations of stars that have completed their life cycle. Start with white dwarfs. These are the exposed cores of low to medium mass stars, like the Sun, after they shed their outer layers as planetary nebulae. A white dwarf is about the size of Earth, but with mass around that of the Sun, incredibly dense. Our galaxy is teeming with them. Every star less than about 8 times the mass of the Sun will end as a white dwarf. Given the Milky Way's age, billions of such stars have already gone through that process. It's estimated there are many billions of white dwarfs in the Milky Way. They quietly cool and fade over time, a process that takes longer than the current age of the universe to go completely dark. So even the oldest white dwarfs, perhaps 12 billion years old, still glow faintly red or infrared. In the thick disk and halo, one can find very old, cool white dwarfs that are barely luminous. These are sometimes called black dwarfs in the making, though not fully black yet. The Hubble Space Telescope has observed some of these ancient white dwarfs in globular clusters, giving us clues to ages. They're neutron stars. These are the collapsed cores of massive stars, 8 to 20 solar masses originally, that went supernova. They cram more mass than the Sun into a sphere only about 20 kilometers across. A neutron star is so dense that a teaspoon of its material would weigh billions of tons. There are likely hundreds of millions of neutron stars in the galaxy, though we only detect those that reveal themselves via radio pulses or X-ray emission, etc., a small fraction. Many neutron stars are observed as pulsars, lighthouses of radio or even optical X-ray beams sweeping the sky. The Milky Way pulses with thousands of known pulsars, each a neutron star spinning rapidly. Some spin hundreds of times per second, millisecond pulsars, often found in globular clusters or as remnants of certain binary evolution channels. These are like cosmic clocks, and they even help us detect gravitational waves' background or probe the interstellar medium via dispersion of their signals. Neutron stars also can be in binary systems. Sometimes 2 neutron stars orbit each other. We've detected those by their gravitational wave in spiral, like the famous one that produced both gravitational waves and a gamma-ray burst observed in 2017. Some neutron stars pull gas from a companion, flaring as X-ray binaries or even undergoing occasional outbursts when that gas triggers nuclear fusion on the neutron star's surface. These are X-ray bursters. And then, black holes. Aside from the supermassive one at the center,
The Milky Way is littered with stellar mass black holes, formed by the collapse of stars above roughly 20 solar masses, or from mergers of neutron stars, etc. How many black holes? Possibly tens of millions. Each typically 5 to 15 times the Sun's mass, some more if formed by mergers. They are invisible unless actively accreting, pulling in gas, which then emits X-rays. Many have been found as X-ray binaries, where a black hole orbits a normal star and strips gas from it, forming a hot accretion disk that emits X-rays. Famous examples: Cygnus X1, the first strong black hole candidate, which is a stellar black hole consuming mass from a blue supergiant, or V404 Cygni, another volatile black hole binary that has dramatic outbursts. Most stellar black holes, however, might just roam quietly. One was recently found via gravitational microlensing. It passed in front of a background star, and the star's light brightened as the black hole's gravity bent it. That was our sign of an isolated black hole. The detection suggested a 7 solar mass black hole about 5,000 light away, dark and solitary. These remnants, white dwarfs, neutron stars, black holes, essentially form a kind of invisible substructure in the Milky Way. If you could see them all with some special glasses, the galaxy would have a faint glow or speckles from myriad white dwarfs in the disk and bulge, little spark-like pulsar beacons, point-like masses warping light, black holes. There's even speculation about intermediate mass black holes, hundreds to thousands of solar masses, possibly lurking in the centers of some globular clusters or dwarf satellite cores. We should also consider black hole binaries merging. LIGO detects such events likely from distant galaxies, but they could happen in our galaxy too, though none detected from within our galaxy yet, because they are rare per galaxy. If two black holes merge in Milky Way, it would release a burst of gravitational waves that we could detect. And neutron star mergers, aside from gravitational waves, they can eject heavy elements. So some of the gold or platinum on Earth might owe to a neutron star collision in the Milky Way's past that seeded heavy elements into a gas cloud that formed our solar system. The presence of remnants also provides continuity. A star dies, but part of it lives on as a remnant. For example, when the star that went supernova to create the Crab Nebula did so in 1054 AD, seen by Chinese astronomers as a guest star, it left behind the Crab pulsar, which still spins and powers the nebula's glow. The Milky Way likely experiences a supernova roughly once every century or so, though it's been a while since one seen by the naked eye, possibly because dust obscured a few. Each supernova adds a neutron star or black hole to the population. Also consider planetary nebulae, the colorful shells of gas from red giants casting off their layers. At the center of each is a new white dwarf. The galaxy has thousands of planetary nebulae visible, each an announcement: a white dwarf is born here. They are ephemeral. The nebula fades after 10,000 years, leaving just the white dwarf. The distribution of remnants is interesting. White dwarfs are everywhere: thin disk, thick disk, bulge, reflecting where stars like the Sun and smaller have lived and died. Neutron stars and black holes are mostly from massive stars, which mostly form in the disk, spiral arms. So their remnants should be in the disk, though some get kicked at birth. Pulsars often have high velocities due to supernova kicks, launching them out of the plane. Some even escape the galaxy if the kick is strong. So neutron stars might have a thicker distribution due to kicks. Black holes might get smaller kicks, maybe some kicks if asymmetry in supernova. So there could be black holes sailing in the halo or escaping as well. One evocative element: some remnants become zombie stars. White dwarfs can accrete material from companions, and if they reach 1.4 solar masses, Chandrasekhar limit, they explode as type Ia supernovae, which are important standard candles for cosmology. So even after death as a white dwarf, a star might have a spectacular thermonuclear rebirth explosion. Neutron stars too can have second lives, spinning back up by accreting matter, Millisecond pulsars are old neutron stars sped up by binary accretion, turning them into whirling beacons again. And black holes might occasionally flare if they consume a passing gas cloud, or even tear apart an unlucky star that wanders too close. Though that's more for big BHs like the center BH. Stellar black holes have small reach, but can still disrupt planets or smaller stars maybe. So, the Milky Way is somewhat of a graveyard entwined with a nursery. New stars are born from gas, often enriched by the deaths of old stars. And the dead stars themselves persist as these remnants, continuing to contribute gravitationally and sometimes in energy outbursts. Even smaller remnants, brown dwarfs, failed stars, substellar objects, and black dwarfs, cooled white dwarfs, none yet fully black, could be considered part of the population of faint objects bridging the gap between stars and remnants. Brown dwarfs are like forever fetal stars that never ignited hydrogen. There are likely as many, if not more, brown dwarfs than stars, lurking with low heat and faint infrared glow. They're not remnants, since they never fully were stars, but they add to the inventory of dark objects. The interplay of remnants could also create exotic phenomena. For example, a neutron star and a white dwarf binary, or a black hole swallowing a neutron star, could produce interesting events like gamma-ray bursts, though those typically happen in distant galaxies. Philosophically, the existence of these remnants is a reminder of mortality and memory. The Milky Way carries its dead with it. Unlike living creatures where corpses decay and disappear, in the galaxy the corpses remain for eons, influencing the environment. The remnants contain clues of their progenitors, like pulsars have spin rates and magnetic fields telling of the original star's core. White dwarfs have composition layers that tell of how the star ended nucleosynthesis. One might imagine each remnant as a kind of memory stone. If we could read them perfectly, we'd know about the star that once shone. Some white dwarfs have atmospheres of hydrogen or helium or carbon, telling what outer layer was left. Some neutron stars have extreme magnetic fields, magnetars, hinting at properties of the collapsed core. As we sail around the galaxy, every now and then we might pass invisible mass points, a black hole here, a neutron star there. Only a chance X-ray or radio emission or gravitational lens effect gives them away. Also, not to forget supernova remnants, not the compact object, but the blast wave and expanding cloud of gas like the Veil Nebula or Cassiopeia A's shell. These are ephemeral compared to the remnant core, but they, for a few thousand years, mark the spot of a stellar death like a wreath. The galaxy has many supernova remnants, observable in radio or X-ray, many more unobserved likely. They contribute to heating cosmic rays, etc. Thus, black holes and remnants add a quiet, somber layer to the Milky Way's composition. Unseen but present, silent but significant. They also connect to next topic, the central black hole we covered, and the future collision with Andromeda will eventually see black holes merge too, the central ones. But first, let's focus on that future collision. However, perhaps it's good narrative to mention, as time goes on, these remnants accumulate. Far in the future, after star formation ceases, trillions of years ahead, the galaxy will be mostly remnants. White dwarfs turn to black dwarfs, neutron stars cooled, maybe proton decay gone, black holes slowly evaporating via Hawking radiation over unimaginable times. That's the ultimate fate scenario. So in a way, these remnants are hints of what the galaxy will become in the distant, distant future. A graveyard with no new stars, just ghosts slowly fading. But before that final fade out, a dramatic event awaits. The collision with Andromeda, M31. That's a nearer term, in billions of years, future, that we should explore now. The future collision with Andromeda. In the cosmic dance of galaxies, the Milky Way and the Andromeda galaxy, our nearest large neighbor, are destined to collide. It's a fate set by gravity, a meeting foretold by the motions we observe today.
Approximately 4 billion years from now, when our sun will be approaching old age, the serene night sky as we know it will undergo a radical transformation as Andromeda draws near, eventually merging with the Milky Way in a grand embrace. Let's set the scene. Andromeda, also called M31, is currently about 2.5 million light-years away, visible as a faint smudge in the constellation Andromeda. It's a spiral galaxy, somewhat larger than the Milky Way, perhaps containing 1 trillion stars. We are on a slow collision course. Andromeda is moving towards us at about 110 kilometers, as seen by the blue shift of its light. There's also likely some sideways motion, but even with that, simulations suggest a collision is likely given the strong gravitational attraction within our local group. Fast forward a couple billion years. Andromeda looms larger in the sky. To future inhabitants of Earth, if any remain or if Earth is still habitable then, as the sun will be heating up, Andromeda might appear as a giant spiral, filling a good portion of the sky, growing brighter and more detailed each eon. Its spiral arms could become discernible, and its central bulge would shine like a hazy second Milky Way band across the heavens. As the two galaxies near, their gravitational interactions will begin to disrupt both. Long before the cores meet, their halos and outer disks will clash. Gas clouds in the outer regions might slam into each other, triggering bursts of star formation. So we may see bright new star clusters and nebulae igniting in the collisional interface. The sky might become littered with brilliant O-type star clusters as the galaxies disturb each other's gas. Eventually, the galaxies will interpenetrate. Unlike a car crash, stars mostly do not hit stars because of vast distances between them. Instead, the two stellar disks will pass through each other like ghosts, but gravity will yank on each component, distorting shapes. Tidal tails of stars might fling outwards, great arcing streamers thrown into intergalactic space. Perhaps some stars, and potentially their planetary systems, will be tossed into new, wildly different orbits, some even ejected into space. Our solar system might be largely unaffected physically. The chance of direct close encounters with another star is small even in a merger, though not zero. But the night sky would be chaotic, new constellations of unfamiliar stars, as Andromeda's stars mix with ours. The black holes at each galaxy's center, each millions or billions of solar masses, will spiral toward each other over time, eventually coalescing into an even more massive black hole, after performing a sort of gravitational dance that radiates gravitational waves. When those two black holes finally merge, they will send ripples through space-time. Some future gravitational wave observatory might detect the echo of that event if any observers remain. The merged black hole will likely become active, consuming gas shaken into the center, perhaps lighting up as a quasar for a short time, shooting jets of radiation. During the interaction, the structure of both galaxies changes. The orderly spiral patterns will become twisted and then dissolved. Over a few billion years of alternating passes, these collisions often involve the galaxies swinging through each other, then slowing, coming back for another pass, like oscillating before finally coalescing. The stars' orbits will randomize. Eventually, what emerges from the wreckage is not a spiral galaxy at all, but probably a giant elliptical galaxy, a more amorphous, three-dimensional ball of stars with no distinct disk or arms. This new galaxy has been nicknamed Milkomeda by some, a portmanteau of Milky Way and Andromeda. It will contain nearly all the stars of both galaxies, plus any satellites involved, but arranged in a new way, many on long eccentric orbits forming a huge elliptical distribution. The gas, much of it likely either used up in starbursts or heated and expelled, might not form a disk, so star formation might slow drastically after the merger consumes the easily formed stars. For any beings at that time, the concept of the Milky Way or Andromeda as separate entities will be meaningless. There will be just one great galaxy filling the sky with a golden glow of billions of stars in every direction. This collision is not something to fear on a human timescale. 4 billion years is far beyond human or even Earth's future.
the Sun will be in a red giant phase in about 5 billion years, possibly swallowing Earth. But as part of the galactic story, it's a dramatic climax. Our galaxy, which has been relatively isolated aside from munching dwarfs, will meet its equal and merge, fundamentally altering its identity. Interestingly, the merging will likely bring in Andromeda's own retinue of satellites, and our own, mixing them all. Maybe the Triangulum galaxy, M33, another member of the local group, will get involved or orbit the merger. Many of the satellite galaxies might either merge into the big one or remain as orbiting clusters of stars or get flung out. From a vantage point within the merging galaxies, cosmic events like starbursts might be visible. Perhaps multiple supernovae popping off as new massive stars quickly evolve. Globular clusters could be jostled, and some might be thrown into intergalactic space or form anew from colliding gas clouds. The night sky during the merger would likely have many more bright stars due to starbursts and diffuse light from the mass of stars. Perhaps the concept of night might get a bit eroded at some phases as more light fills the sky. However, given the scales, even a merger wouldn't make the sky bright like day. It'd just have more interesting features. Galactic collisions also produce rings and shells sometimes in the stellar distribution, visible long after, and trails of stars might form tidal streams connecting outward. Once the dust settles, literally, much dust might be cleared by starbursts and AGN feedback. The new combined galaxy will shine for trillions of years as it slowly uses remaining gas, then coast into a long, dark era. But by then, local group has become one big, gravitationally bound island universe. And due to the accelerating expansion of the universe, distant galaxies would have receded beyond visibility. So in far future, the merged galaxy will be quite alone in terms of observable universe, apart from maybe its local cluster. But focusing back on now, the knowledge of this future event is one of the marvels of modern astronomy. We have essentially predicted a cosmic event far beyond any human timeframe. It gives a sense of inevitability, but also continuity, that the cosmos has its timetable and flows that will go on without us. If we put ourselves poetically into that future scenario, try to imagine Earth's sky, say 3.75 billion years from now. Andromeda's disk spans the sky, maybe tens of degrees across, a glittering spiral visible even in daylight, perhaps as a faint structure. Then, in 500 million more years, the first close pass occurs. The sky might erupt with new stars. Perhaps the Milky Way's band in the sky distorts into weird shapes as Andromeda's stars join it. In 1 billion more years, multiple bands or a chaotic scatter of stars overhead as everything mixes. By 6-7 billion years from now, a smooth, glowing ellipsoidal distribution of light in the sky with no Milky Way band at all, just an all-sky faint glow, maybe thicker toward the center of the new galaxy. All the while, as an observer, you would have had to withstand the sun's red giant expansion, etc. But perhaps humanity's far descendants could watch from some other corner, or through robotic eyes. It's a scene for science fiction, but one grounded in astrophysics. Galactic collisions are common in the universe. Many galaxies we see are in collision or merged. Our own just hasn't had a major collision recently. The last big one might be that Gaia Enceladus event 10 years ago. So the Milky Way has had time to be a nice spiral. Andromeda too had mergers.
It has a big bulge indicating past action. Now these two big ones will make one larger elliptical. Ellipticals typically have older stars and less gas afterwards.
One could wonder about life consequences. Any risk to the solar system? Direct collisions of stars are extremely unlikely. However, passing stars could disturb the Oort cloud, comets, and send comets inward, raising the risk of impacts for planets. Also, if the sun's orbit is altered, it could experience changes in environment, maybe moving to a region with more supernovae or radiation. It's possible that life on Earth by then is gone due to sun's evolution, but if not, the merger could bring some gravitational nudges. But Earth's existence is precarious with the sun's changes anyway. Our collision with Andromeda is often portrayed as violent, but in human terms, it's a slow-motion event spanning billions of years. It will not destroy either galaxy entirely, but transform them. It is an act of creation as much as destruction, creating a new galaxy from two. As we consider that future, it's a reminder that change is the constant. Even the majestic spiral of the Milky Way is transient on cosmic time. The cosmos builds and rebuilds structures over time. Nothing stays the same. Galaxies grow, merge, fade. Now, coming back to a present perspective, one might ask, how fast are we moving right now and toward what? Which leads to consider the speed of motion more generally, not just relative to Andromeda, but all the motions we partake in. We have touched on orbital speeds around the galaxy, but perhaps dedicate a section to the myriad motions, the speed of stars, of the sun, of the galaxy moving through the universe, etc., to capture the dynamic nature. In the beginning, there was darkness. For a long age after the birth of the universe, no stars shone, no galaxies twirled. Only darkness and silence stretching across an unfathomable expanse. The cosmos was newborn and without form, filled with diffuse clouds of hydrogen and helium gas, remnants of the Big Bang. There were no twinkling lights, no warmth, only the faint afterglow of creation cooling into night. Imagine that primordial darkness, a universe waiting, quiescent and still, with all its future potential sleeping in invisible clouds. But even in that silence, gravity was at work. Slowly, imperceptibly, it drew the primordial gas into filaments and clumps, coaxing the first structures to form in the void. Over eons, these clumps grew denser and hotter at their centers. Deep within one such gathering of gas, pressure and heat built until something new and miraculous occurred. Nuclear fusion ignited. There, in the bleak darkness, a tiny point of light flared into being. The first star had been born. In that moment, the universe was no longer lightless. A spark had appeared in the cosmic night. With that first star, the cosmic dawn broke. One solitary star poured out light and heat, pushing back the blackness around it. And soon, another star lit, and then another, scores of them, flickering on in the cosmic night. What had been endless darkness was now speckled with faint starlight. These first stars were unlike the stars we know today. They were giants of pristine hydrogen and helium, born in a virgin cosmos. They burned with brilliant blue-white fire, immensely hot and massive. Their intense ultraviolet light flooded into the surrounding gloom and began to clear away the primordial fog of neutral hydrogen that filled space. For the first time, light moved freely through the cosmos, illuminating it on a grand scale. The cosmic dark ages were ending. The universe was beginning to reveal itself in starlight. These first stars lived fast and died young. After only a few million years, brief by cosmic standards, their central fuel was exhausted. In their cores, they had fused hydrogen into helium and helium into carbon and other heavier elements, forging the first atoms of carbon, nitrogen, oxygen, and more. When fusion could proceed no further, the balance that held them up faltered. The stars met their end in colossal explosions. One by one, the primordial giants tore themselves apart as supernovae. Each such explosion was titanic. Momentarily, a single star's death could outshine an entire galaxy. The night that had been gently lit by starlight was suddenly ablaze with a ferocious flash. Then, as the supernova faded, darkness returned. But it was not the same darkness as before. Now, it was enriched by the scattered ashes of stars, the gaseous debris of those first supernovae, carrying newly forged elements, mixed back into the cosmic gas, seeding the universe with the ingredients for future worlds. Meanwhile, gravity continued its creative work on larger scales. The first stars had formed in small proto-galactic clumps,
and gravity drew these clumps together. They merged and coalesced into the first galaxies, swirling assemblies of stars, gas, and dark matter. The once empty universe was now dotted with infant galaxies, and each new galaxy sparkled with the light of millions of stars. Over billions of years, galaxies grew by merging with each other and forming new stars within. The cosmos transformed from a dark, simple expanse to a richly structured tapestry. By a few billion years after the beginning, the cosmic web of galaxies stretched across space, filaments of glimmering light tracing gravity's hand. Generation after generation of stars continued to be born and die within these galaxies, steadily enriching and shaping them. The universe's early thin gases had become a complex network of stellar cities, glowing with billions of points of light. Let us drift into one such galaxy, a spiral galaxy not unlike our own Milky Way, at a time when the universe is mature and full of stars. Within one of its graceful spiral arms lies a vast, cold cloud of molecular gas and dust, tens of light years across. It is dark and opaque, a silent nebula hiding new wonders inside. This is a stellar nursery, a place where new stars will be born. For ages, this cloud has floated in the galactic disk, nudged by passing spiral density waves and perhaps stirred by ancient supernova shockwaves. Now, regions within it begin to collapse under their own gravity. Deep inside, dense knots of gas form, each destined to become a star or a group of stars. All through the cloud, multiple embryos of stars are taking shape, though they are hidden from view by the dusty shroud. In one region, a particularly dense clump, perhaps a few dozen times the mass of our Sun, contracts and fragments. At its center, material compresses into a smaller, hotter protostar. Change is coming to the darkness of this nebula. At first, the forming star is shrouded. It is a protostar, not yet fully born, growing as it pulls gas from the surrounding cloud. It spins faster as it contracts, and a rotating disk of gas and dust forms around it. Twin jets of hot gas shoot out from its poles, tunneling through the cloud. Deep inside, the temperature climbs higher and higher. For tens of thousands of years, a mere moment in cosmic time, this protostar gathers mass in the darkness, heating up steadily. When its core temperature reaches about 10 million degrees, a great transformation occurs. Hydrogen nuclei begin to fuse into helium. In a sudden burst of energy, true starlight ignites in the core. The protostar has become a star. Outward pressure from this newborn star's core now halts any further rapid collapse. The star's fierce light and stellar winds blow away the cocoon of dust and gas that enveloped it. At last, the new star emerges from its birth nebula, announcing itself with brilliant light. The surrounding leftover gas, bathed in the star's intense ultraviolet radiation, begins to glow. What was once an invisible, cold cloud now shines as an ionized nebula, like a cosmic neon sign, its hydrogen gas fluorescing pink and red. A dark corner of the galaxy has given birth to a beacon of light. In the surrounding cloud, other newborn stars are likely emerging as well, turning the nebula into a cradle of suns. Indeed, stars are often born in litters. The collapse of one part of a cloud usually means many fragments produce protostars in the same region. As our star bursts forth, it is joined by dozens or hundreds of sibling stars, all coming to life together from the same cloud. Together, they form a young star cluster, a sparkling group of newborn suns of various masses. They blaze hot and blue, their combined radiance blowing the remaining nebular material into filaments and wisps. One can imagine the scene, where there was darkness and dust. Now there is a cluster of radiant stars, their light reflecting and refracting in the thinning veil of gas. The stellar nursery has become a celestial nursery rhyme of light, a beautiful, chaotic region celebrating the arrival of new stars. For a time, these siblings remain clustered, bound by the gentle gravitational pull they exert on each other. They drift together through the galaxy as a loose family known as an open cluster. In the cluster's early life, it is a stunning jewel box of brilliant stars, all relatively close in space. Yet, over hundreds of millions of years, this family will gradually disperse. Gravitational nudges from passing stars and clouds, as well as internal interactions, will cause members to wander away one by one. The cluster's members, once tightly knit, become strays, settling into their own orbits around the galaxy, mingling with billions of other solitary stars. This is the fate of most open clusters. They are transient gatherings that eventually dissolve into the galactic population. Our own sun likely shared this fate. It was almost certainly born in a cluster with many siblings, stars that formed from the same cloud some 4.6 billion years ago. Over time, that original cluster dissolved. Today, the sun roams the galaxy alone, and the stars that were born alongside it have long since scattered. A few of the sun's lost siblings may have been tentatively identified by their chemical signature, but most are strangers now far across the sky. Still, it's a profound thought. The sun's family of origin has dispersed, yet the galaxy is now sprinkled with those related stars, each carrying the same ancestral imprint in their atoms. In a sense, every star eventually becomes an orphan, blending into the vast community of the Milky Way. Some star clusters, however, are so massive and tightly bound that they can survive for billions of years. These are the globular clusters, ancient, spherical hordes of stars that reside in the outskirts, halo, of galaxies. A globular cluster might hold hundreds of thousands of stars crammed into a ball only a few hundred light years across. The stars inside are extremely old, many formed during the early eras of the galaxy. They shine mostly with a warm reddish glow, having long ago lost their bluer, short-lived members. The stars in globular clusters are almost pure hydrogen and helium, containing only tiny traces of heavier elements, which tells us they were born before later generations of stars had seeded the galaxy with metals. They are truly relics of the distant past, cosmic time capsules unchanged for eons.
If you could stand on a planet inside a globular cluster, the night sky would be a breathtaking spectacle. Thousands of stars would crowd the heavens, many so bright that even at night they could cast subtle shadows. There might be no true darkness at all. Your sky would be awash with perpetual starry twilight. These ancient clusters have witnessed nearly the entire history of the universe. Some of the stars shining around you in that cluster may have been burning since shortly after the galaxy itself formed. Globular clusters endure as splendid beacons on the fringes of galaxies, their stars bound together in a tight gravitational embrace for billions upon billions of years. Now let us return to our star, the one we followed out of its nebula. It has left its nursery and cluster behind, or its siblings have all drifted away. The star has entered the long, steady adulthood of stellar life. Deep in its core, hydrogen fusion generates a steady outpouring of energy. This energy travels from the core through radiative layers and convective currents, and finally radiates from the star's surface as light and heat. Gravity pulls inward on the star's mass, but the pressure of hot gas and the continuous fusion-powered radiation push outward. These forces balance perfectly. The star settles into a stable state known as the main sequence, where it will spend the majority of its life shining at a nearly constant brightness for eons. It is as though the star has found harmony, a peaceful equilibrium in which it neither collapses under gravity nor erupts from internal fire, but simply glows steadily. Our sun is in this very phase of life. It is a middle-aged main sequence star, quietly fusing hydrogen into helium in its core, as it has for about 4.5 billion years, and will continue to do for roughly another 5 billion. Day after day, it shines with reassuring consistency, its energy nurturing the planets orbiting it. We live in the warm embrace of a stable star.
The sunlight that bathes Earth each day is the product of that core fusion, photons freed from the sun's interior after thousands of years of random walk and an 8-minute sprint across space to our world. This steady radiance has allowed life to arise on Earth, anchoring our existence. The sun, in all its ordinariness, means everything to us. Yet the sun is just one of countless stars on the main sequence, doing the same quiet work across the galaxy.
Even the sun has its subtle rhythms. Its surface seethes with convection, and dark magnetic blemishes called sunspots come and go. Approximately every 11 years, the sun's magnetic activity cycles, leading to periods of many sunspots and flares followed by lulls. Sometimes great arcs of plasma erupt from its surface in solar flares or coronal mass ejections, sending streams of charged particles into space. When these particles wash over Earth, they can spark auroras that dance in our polar skies, a vivid reminder that our seemingly gentle sun has its storms. Still, these variations are minor on the scale of the sun's total output. To our eyes and lives, the sun remains a stable beacon. It is a calm star by cosmic standards, and that calm has been essential for life on Earth to thrive over geological timescales. Not all stars enjoy such tranquility or longevity. The destiny of a star is determined largely by its mass at birth. Mass is the master parameter that dictates a star's temperature, brightness, and lifetime. A very massive star lives dramatically. It burns its fuel at a furious rate, shines brilliantly, and dies young. A small star lives cautiously. It sips fuel slowly, glows gently, and may outlive all other stars. Consider a star 10 times the sun's mass. Its core temperatures are far higher, and it will blaze blue-white, pouring out energy hundreds of thousands of times faster than the sun. But it might last only 20 million years before exhausting its core fuel. Now consider a star 1/10 of the sun's mass, a red dwarf. It is cool, perhaps 3,000 K at the surface, and dim, maybe 1/1000th the sun's luminosity. It will burn its hydrogen so frugally that it can live for hundreds of billions or even trillions of years. The universe itself is not old enough for any such star to have died yet. None of the red dwarfs born at the dawn of time have even begun to flicker. In short, massive stars are the sprinters of the cosmos, and red dwarfs are the marathon runners. Astronomers classify stars by their spectra and temperature. The hottest, most massive stars are O-type, glowing bluish-white and searingly bright. After O come B and A types, still extremely hot and white. F and G-type stars, our sun is a G-type, are intermediate, white to yellow in color and moderate in heat. K and M stars are cooler, orange to red in hue, including the countless red dwarfs. This sequence, O, B, A, F, G, K, M, is essentially a temperature scale from the fiercest blue-white stars to the faintest red stars. And indeed, the night sky shows this variety. Some stars shine with an icy blue tint, others with a golden glow, and some with a faint reddish light. Each color is a clue to a star's inner furnace. A blue star is like a roaring fire. A red star is like a warm ember. The cosmos offers a grand palette of stellar colors and intensities. The sizes of stars also span a tremendous range. Some red supergiant stars have bloated to astonishing dimensions, as much as 1,000 times the sun's radius. If one of those sat where our sun is, its swollen atmosphere would extend beyond the orbit of Mars, perhaps even reaching Jupiter. By contrast, the smallest stars, just above the threshold for sustained fusion, are only a bit larger than the planet Jupiter. One of these tiny red dwarfs, while containing perhaps 8% of the sun's mass, might measure only 1/10 of the sun's width. Between these extremes lie stars of every conceivable size, from giant stars big enough to engulf orbits of planets, to humble dwarves barely bigger than gas giant planets. The diversity is staggering. And if an object is smaller still,
below about 8% of the Sun's mass, it never becomes a true star. It becomes a brown dwarf, a failed star. Such an object doesn't reach the core temperature needed for sustained hydrogen fusion. A newborn brown dwarf may briefly fuse a little deuterium, a heavy form of hydrogen, or simply radiate leftover heat from its gravitational contraction. But before long, it settles into a life of slowly cooling and fading. Brown dwarfs are like cosmic embers. They glow faintly in red or infrared light, but no fire rages within. They fill the gap between the largest planets and the smallest stars. In the galaxy, there may be as many brown dwarfs as stars, lurking dimly in the darkness, detectable only by sensitive infrared eyes. They remind us that nature's categories are fluid. There is a continuous spectrum from planets to stars, with brown dwarfs bridging the two. To the unaided eye across human lifetimes, most normal stars shine with a steady light. But many stars are not truly constant. Some vary in brightness in subtle or dramatic ways. Some stars pulsate in and out like cosmic heartbeats. A classic example is a Cepheid variable, a bright giant star that rhythmically swells and shrinks, causing its brightness to rise and fall over a period of days or weeks. When it expands, its surface cools and it dims slightly. When it contracts, it heats up and brightens. These pulsating stars are so regular that astronomers use them as distance markers. Their pulse period relates to their true luminosity. So by observing their cycle, we can deduce how far away they are. They literally blink out a Morse code that we have learned to read, helping us measure the universe. Other stars vary more erratically. Young stars, still surrounded by disks of gas, can flicker as they accrete material, or as clumps of dust periodically obscure them. Some mature stars erupt in flares, especially red dwarfs, which can unleash powerful stellar flares that make the star momentarily much brighter. Even our Sun is slightly variable. Over its 11-year sunspot cycle, its energy output changes by a fraction of a percent. And in old age, many stars become variable again. Red giants often pulsate with large amplitudes, like mirror variables, taking many months to cycle through a dimming and brightening. Such an elderly star might expand and contract so much that it visibly changes brightness over the course of a year, shedding its outer layers with each pulse. In some cases, a star's light is not changing because of its own behavior, but because of an external effect. Consider binary star systems aligned in our line of sight. When one star passes in front of the other, it eclipses its companion. From Earth, we see the combined light dip periodically, even though each star's intrinsic output is steady. These eclipsing binaries produce regular patterns of dimming and brightening, a stellar blink that can be clockwork precise. By studying such systems, astronomers can learn the sizes of stars and their orbits. In fact, the discovery of planets orbiting other stars often comes from a similar effect. A planet passing in front of its host star causes a tiny eclipse, a minute drop in the star's brightness. Sensitive telescopes can detect that dip, revealing the presence of a world we cannot otherwise see. In this way, the light of stars encodes the presence of their companions, be they other stars or orbiting planets. Indeed, many, perhaps most, stars are not solitary like our Sun, but part of binary or multiple star systems. Two stars bound together will orbit a common center of gravity, like dancers linked by an invisible string. If they are well separated, each evolves individually. But if they orbit closely, their lives can become intertwined in remarkable ways. Imagine a close binary where one star ages faster and swells into a red giant, while the other is still a smaller main sequence star. As the giant grows, its outer layers draw ever closer to the companion star. Eventually, the giant's gravity can no longer hold on to those distended layers. Its material starts flowing onto the companion. A stream of gas begins to pour through the inner Lagrange point, the gravitational gateway between them, forming a luminous accretion disk around the smaller star. Matter spirals in, heating up and glowing brilliantly. The giant star, losing mass, shrinks back somewhat, relieved of its burden, while the companion star gains fresh fuel and becomes hotter or more active. This mass transfer dramatically alters the fate of both stars. If the receiving star in such a scenario is a white dwarf, the dense core of a previously sun-like star, the story takes another turn. The gas dumped onto the white dwarf piles up on its surface. Over time, perhaps years or centuries, enough hydrogen accumulates on the white dwarf's surface to trigger a sudden burst of fusion. In a flash, the layer of accreted gas ignites and detonates, causing the white dwarf to erupt in a nova. The star system that was faint brightens drastically for a little while, as the white dwarf's surface explodes in a thermonuclear flash visible across light years. After venting that energy, the white dwarf settles down and the cycle can begin anew if more gas comes in. In this way, a close binary can produce repeated novae like a recurring stellar heartbeat of explosive energy. In some cases, the white dwarf accumulates too much mass from its companion, beyond a critical limit, about 1.4 times the mass of the Sun. Then the entire white dwarf is overwhelmed by runaway fusion and detonates in one titanic explosion, a Type Ia supernova. In that instant, the white dwarf is obliterated, and a fireball of debris expands outward. Such a supernova can briefly rival a whole galaxy in brightness. Nothing of the white dwarf remains, only a rapidly expanding cloud of ash, rich in iron and nickel, hurtling through space at thousands of kilometers per second. These Type Ia supernovae are incredibly important standard candles in astronomy, yet behind their brilliance is the quiet story of a binary companionship that went to the extreme. Other binary destinies include outright mergers. If two stars in a binary spiral closer, perhaps due to gravitational wave emission or interactions with other stars, they can eventually collide and coalesce. Two main sequence stars merging will produce a single, more massive star, often with a spectacular transient event. Astronomers have observed luminous red novae, believed to be the signature of merging stars. The pair slowly draw together, then suddenly brighten with a red glow as they meld into one. The result might be an oddly bloated star or a fast-spinning object, but a new single star nonetheless. If, on the other hand, the binary is two neutron stars, the dense remnants of supernovae, their merger is even more dramatic. They collide and merge into either a heavier neutron star or a black hole, releasing a burst of energy that can include intense gamma rays and gravitational waves, literally a ripple in space-time that can be felt across millions of light years. Such a merger also forges heavy elements, like gold and platinum, in profusion, seeding the surrounding space with these precious materials. Thus, even in their deathly collision, stars create and share new riches with the cosmos. For long periods in between such events, a solitary star like our Sun just keeps shining steadily. But eventually, even the most stable stars must face an end to their fuel. Our Sun, for instance, after roughly 10 billion years of main sequence life, will deplete the hydrogen in its core. So what happens when a star runs out of its most basic fuel? The answer unfolds in stages, heralding the transition to a star's old age and death. For the Sun and stars of similar mass, this final chapter is both gentle and beautiful. For more massive stars, it is violent and spectacular. When a star like the Sun exhausts the hydrogen in its core, fusion in the core ceases, but fusion still goes on in a shell of hydrogen around the now inert helium core. With the core no longer generating outward pressure, it begins to contract under gravity. That contraction releases gravitational energy, which heats the core and the surrounding shell of hydrogen. The hydrogen shell, now hotter and under higher pressure, burns even more vigorously than the core did. The increased energy output pushes the star's outer layers outward. The star's envelope balloons to enormous proportions. As it expands, the star's surface cools, because the same energy is radiating from a much larger area, and its hue shifts toward red. The star has become a red giant. Our Sun will go through this transformation, swelling perhaps 100 times its current diameter. In those far future days, the Sun's reddish orb could engulf Mercury and Venus, possibly even reaching close to Earth's orbit. Even if Earth is not swallowed, the Sun's expanded atmosphere and intense heat would scorch our planet barren. In any case, the inner solar system will be radically transformed. A person, if somehow observing from a safe distance, would see the Sun change from a small yellow disk to a vast, ruddy sphere that dominates the sky. The once stable star becomes a bloated giant, its core an intensely hot, contracting ball of helium ash. Its outer layers diffuse and cool. Yet paradoxically, the Sun will shine more brightly overall during this red giant phase because its enormous size more than compensates for the cooler surface. It will be majestic and terrifying all at once. Inside the core of the red giant Sun, temperatures continue to climb as the core contracts under gravity's relentless squeeze. When the core reaches about 100 million degrees Celsius, a new kind of fire is kindled, helium fusion. 3 helium nuclei begin fusing together to form carbon in a process called the triple alpha reaction. In stars like the Sun, this onset of helium fusion can occur very suddenly in what's known as a helium flash, releasing an enormous burst of energy in a matter of minutes. However, that energy mostly goes into lifting and expanding the core, not into blowing the star apart. The Sun will then settle into a new equilibrium, a helium-burning star. The core expands and cools slightly after the helium flash, and the star's outer layers contract a bit from their extreme red giant state. The Sun will become a somewhat smaller, though still large, yellow-orange giant, with a core quietly fusing helium into carbon and oxygen. This helium-burning phase is much shorter than the hydrogen-burning main sequence, perhaps only a few tens of millions of years for a star like the Sun. Eventually, the helium in the core is exhausted as well. Now the core of the Sun will be made primarily of carbon and oxygen, the ashes of the helium-burning phase. The core again lacks an energy source and begins to contract yet further. For a star of the Sun's mass, it will not reach the temperature needed to ignite carbon fusion. Fusion will continue only in shells around the core, a shell of helium fusing into carbon just outside the core, and a shell of hydrogen fusing into helium above that. The star responds by expanding again. It enters a second red giant phase, the asymptotic giant branch phase, swelling even more dramatically than before. The Sun will become extremely large and luminous, but also unstable. Its outer layers are only loosely bound now, and strong pulsations set in, causing the star's brightness to vary and its layers to puff outward and then fall back cyclically. During this time, the Sun, or any star in this phase, will begin to undergo significant mass loss. Each pulsation in the star's envelope helps throw some gas into space. The star also generates a slow but intense stellar wind, a stream of particles that drags away the star's outer atmosphere. The once robust star is quite literally blowing itself apart, bit by bit. Over tens of thousands of years, the Sun will shed a substantial fraction of its mass. Those outer layers drift away into space, forming an expanding cloud of gas around the star. As more material is lost, eventually the star's hot, naked core becomes exposed, illuminating the receding layers from within. The Sun will no longer be a red giant, but a small, incredibly hot star at the center of a growing gaseous shell. What forms is one of the most beautiful phenomena in astronomy, a planetary nebula. Despite the name, a planetary nebula has nothing to do with planets. The term arose because through early telescopes, these round gas shells looked a bit like planetary disks. It is the glowing remnant of a star's atmosphere, cast off into space. The emerging stellar core at the center may be tens of thousands of degrees hot and emits strong ultraviolet radiation.
This radiation ionizes the expanding shell of gas, causing it to fluoresce in vibrant colors, soft greens and reds from oxygen and hydrogen, for example. Planetary nebulae come in many shapes: spherical shells, ring-like structures, hourglass forms, even complex symmetrical patterns sculpted by magnetic fields or binary companions. They last only tens of thousands of years before the gas disperses into the interstellar medium. But while they shine, they are among the most beautiful sights in the cosmos, the very soul of a star laid bare in color and light. Our sun's planetary nebula might appear as a shimmering halo in the sky, a final gorgeous adornment to mark the end of the sun's life as a star. This nebula will expand and dissipate into the interstellar medium over perhaps 10 or 20,000 years, mixing its enriched gases with the cosmic clouds that will someday form new stars. At the center of the planetary nebula remains the core of the star, a dense, hot sphere about the size of Earth, composed mostly of carbon and oxygen. This is the final state of the star, a white dwarf. A white dwarf no longer has fusion occurring in its core. It is supported against further collapse by quantum degeneracy pressure of electrons, a rather exotic form of pressure that doesn't depend on heat. When it first forms, a white dwarf is extremely hot, well over 100,000 K, and it glows white-blue with residual heat. Over billions of years, it will radiate that heat away and cool down, becoming yellow, then red, and eventually fading to black, an exotic cold crystal of carbon and oxygen in the far future, sometimes poetically likened to a giant diamond in space. However, the universe is not old enough for any white dwarfs to have cooled to the black dwarf stage yet. Even the oldest white dwarfs still shine faintly with leftover heat. The white dwarf that remains of our sun will be incredibly dense. More than half the sun's mass is crammed into a sphere the size of Earth. A single teaspoon of its material would weigh billions of kilograms. It's an object not unlike a planet in size, yet containing the mass of a star. It will slowly cool and dim, perhaps taking tens of billions of years to become truly dark. In the meantime, the legacy of the sun lives on. The planetary nebula it ejected enriches the galaxy with elements like carbon and nitrogen that were made in its core, and the white dwarf stands as a testament to the star that once was. This is the gentle end that awaits stars of modest mass, a quiet shedding of beauty and a final fade into darkness. But what of the giants? The massive stars that lived only a few million years on the main sequence and then grew into supergiants. They face a far more dramatic end. A star significantly heavier than the sun, say 8 times the sun's mass or more, will go through similar stages, hydrogen to helium, helium to carbon, and so on. But it doesn't stop at carbon. After the red supergiant phase begins, its core, much more massive than the sun's ever was, keeps contracting and heating. It ignites carbon fusion when helium is depleted. Then it forms a core of oxygen neon magnesium, which in turn, when exhausted, leads to neon burning, producing oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Finally, silicon burns into iron. The star develops onion-like layers. At the center, an iron core. Around that, a shell of silicon fusing to iron. Above that, a shell of oxygen fusing to silicon. Then a carbon-burning shell. Then a helium-burning shell. Then a hydrogen-burning shell at the exterior. Each stage of fusion releases energy, except the last. And for a time, each supports the star. But the cycles accelerate. Carbon may burn for 1,000 years, neon for a year, oxygen for mere months, silicon for days. The iron core grows rapidly as silicon burning dumps iron ash into it. And then the star reaches the final limit. The iron core grows so large, around 1.4 solar masses, that it can no longer support itself. Iron is a nuclear dead end in a star's life. Fusing iron atoms doesn't yield energy, it consumes energy. So once the core is largely iron, the star has no further fuel to tap
that can hold up the core. In the heart of the massive star, in the span of a second or less, everything changes. The iron core, about the size of Earth and incredibly dense, billions of kilograms per cubic meter, collapses under its own weight. Electrons and protons in the core are crushed together, forming neutrons and releasing neutrinos. The core's collapse accelerates until it is stopped by the most fundamental forces, the strong nuclear force and neutron degeneracy pressure. What was an iron core a few thousand kilometers across is now a ball of neutrons, only perhaps 20 kilometers in radius, a nascent neutron star. The infalling material of the star's inner layers crashes onto this incompressible core and rebounds. A powerful shockwave forms, but at first it stalls within the star. Then, aided by an immense flood of neutrinos pouring out of the core, trillions of neutrinos blasting through each square centimeter, depositing energy, the shockwave regains strength and punches outward. In a magnificent catastrophe, the star explodes. This is a core collapse supernova, the violent death of a massive star. In that instant, the star is obliterated. The outer layers are catapulted into space at a significant fraction of the speed of light. The energy released is almost unfathomable. For a few brilliant days or weeks, the exploding star can outshine the entire galaxy that once humbly hosted it. If such a supernova occurred within, say, 100 light-years of Earth, it would appear brighter than the full moon and could potentially wreak havoc on our biosphere. But typically, these explosions occur safely distant, turning up as new stars in the sky, recorded by astonished observers across history. In 1054 CE, Chinese astronomers recorded a guest star that remained visible in daylight for weeks. This was a supernova in our own galaxy. Even today, nearly 1,000 years later, we see the expanding debris of that explosion as a faint, glowing cloud in the constellation Taurus. In 1604, European observers witnessed another brilliant new star in the Milky Way, which was likewise a supernova. And in 1987, a supernova blaze in a neighboring galaxy, the Large Magellanic Cloud, was visible to the naked eye. These rare events left a deep impression on those who saw them. When the supernova's glare finally subsides, it leaves behind a rapidly expanding shell of gas and dust, a supernova remnant, and, at its heart, the crushed core, either a neutron star or a black hole, depending on the mass. The supernova remnant is a spectacular thing in its own right. The ejected gases, enriched with heavy elements forged in the final moments of the star, like nickel, cobalt, and iron, rush outward and collide with the surrounding interstellar medium. They form glowing filaments and shock fronts that can remain visible for tens of thousands of years. Telescopes today reveal delicate tendrils and wisps of glowing gas in these remnants, beautiful and haunting, the ashes of a star spread across light years. These filaments gradually mix with the general galactic gas. The elements they carry, oxygen, carbon, silicon, iron, and more, become part of the raw material for new stars and planets. Thus, a supernova is both an ending and a new beginning. The star is gone, but its material is now free to join new cosmic structures, and even one day, to become part of new living worlds. At the center of a supernova remnant lies whatever remains of the star's core. If the progenitor star was not too extremely massive, perhaps up to 20-25 solar masses, this remnant will be a neutron star. If the star was more massive, the core collapse likely continued until a black hole formed. Let us consider the neutron star case first. A neutron star is one of the strangest objects in existence. Imagine compressing the sun into a ball only 20 kilometers across, the size of a city. At that density, a single teaspoon of neutron star material would weigh billions of tons on Earth. The gravity at its surface is so intense that if an object were dropped from 1 meter above the surface, it would hit the surface in a microsecond, releasing as much energy as a large bomb. Yet, Despite these extreme properties, neutron stars are real, and we detect them regularly. Many neutron stars reveal themselves as pulsars.
When a massive star's core collapses to a neutron star, it often retains much of its rotational momentum in a greatly shrunken form, so it spins extremely fast. Imagine a star spinning once every 30 days, like our Sun, collapsing to an object only 20 kilometers wide. Conservation of angular momentum would make it spin perhaps hundreds of times per second. Indeed, many neutron stars spin at least dozens of times per second when born. They also can have intense magnetic fields, trillions of times stronger than Earth's. These magnetic fields, anchored in the dense star, accelerate particles and create beams of radiation from the neutron star's magnetic poles. As the neutron star spins, these beams sweep around like the light from a lighthouse. If Earth lies in the path of these beams, we observe a pulse of radio waves, light, or X-rays with each rotation, hence the name pulsar. Some pulsars spin with astonishing speed. A millisecond pulsar can rotate over 700 times in 1 second. Their regular flashing is so precise that pulsars rival atomic clocks in stability. They are nature's metronomes. When pulsars were first discovered, their signals were so regular that some jokingly labeled them LGM for little green men, suspecting an intelligent origin before natural causes were understood. Now, pulsars help us probe extreme physics and even detect gravitational waves indirectly through changes in their orbits. A lone neutron star will gradually cool and slow down over millions of years, becoming fainter and less active. Some neutron stars have magnetic fields so strong that they occasionally fracture their own crusts in starquakes, producing bursts of high-energy radiation. These are called magnetars, and they are the most magnetic objects known. But even magnetars eventually calm as they lose energy. In the fullness of time, a neutron star might become a cold, inert sphere of neutron matter, drifting through the galaxy. Yet it will remain, essentially forever, as a remnant of its parent star, a cosmic tombstone marking where a mighty star once shone. If the core of the collapsing massive star was above the neutron star limit, around 2-3 solar masses, gravity wins an even more final victory. The core continues to shrink past the neutron star stage and becomes a black hole. This is the most extreme outcome of stellar death. The entire mass of the core collapses to an infinitely small point, as far as our physics can describe, and a region of space-time is created from which nothing can escape. A black hole is not a solid object, but rather a region, bounded by the event horizon, beyond which escape velocity exceeds the speed of light. Whatever remains of the star's core resides in that region, forever cut off from communication. In effect, the star's mass punches a hole in the fabric of the universe. All we can observe is the gravitational field it leaves behind, and perhaps X-rays or jets from materials spiraling into it from outside. If the black hole is alone, it may be nearly impossible to detect, as it emits no light of its own. But if it has a companion star or is surrounded by gas, that material can form a hot accretion disk as it funnels into the black hole. Friction and extreme gravity heat the disk to millions of degrees, causing it to glow in X-rays. Sometimes, as the disk material swirls inward, the black hole's magnetic and rotational effects can launch jets of particles at nearly light speed from the poles. These relativistic jets can extend for light years, a ferocious announcement of a black hole's presence. Yet, despite such displays, the black hole itself remains unseen. Only its influence on nearby matter and space-time is evident. It's a silent well in the fabric of reality, a gravitational ghost marking where a star once radiated. In either case, neutron star or black hole, the core collapse supernova has transformed the star and distributed almost all of its substance back into the cosmos. And that is perhaps the greatest significance of these mighty events. They are creators in destruction's clothing. In the furnace of the supernova, and in the neutron star mergers we discussed, many of the universe's heaviest elements are forged. The gold in your jewelry, the iodine in your thyroid, the uranium in the Earth's crust. These atoms were synthesized in the intense crucibles of exploding or colliding stars. The calcium in your bones was formed in a long-dead red giant. The iron in your blood was made in the core of a massive star and distributed by a supernova. Stellar lives and deaths are directly responsible for the elemental richness that enables planets and life. Without generations of stars cooking simple hydrogen into heavier elements and then ejecting them, a planet like Earth could never exist. The universe's first stars had no solid planets around them. There was nothing solid to form rocks or life. It took billions of years of alchemy in stars to brew the ingredients of biology and geology. Thus, each generation of stars leaves a legacy for the next. The gas between stars, the interstellar medium, grows increasingly enriched. Young stars that form now have subtle amounts of iron, silicon, oxygen, and other elements mixed into the primordial hydrogen and helium because they draw from clouds seeded by prior supernova and stellar winds. Our Sun, for example, contains about 2% of these heavier elements, metals in astronomer speak, whereas a first-generation star had virtually none. That 2% might sound small, but it's critical. It's the material that formed Earth and our bodies. In a cosmic sense, later stars carry the DNA, so to speak, of earlier stars within them. Every star that dies writes part of its story into the next generation's composition. We see this continuity everywhere. In regions where massive stars recently died, we often find new star formation triggered by their explosive energy, like flowers blooming after a forest fire. The shockwave from a supernova can compress nearby clouds of gas, spurring those clouds to collapse into new stars. The intense radiation from young hot stars in turn can erode and sculpt neighboring clouds, sometimes stimulating further clumping and star birth at the cloud's edges. It's an intricate cycle, star death leading to star birth, a cosmic phoenix rising from the ashes. Through this ongoing cycle, the galaxy's supply of gas gradually diminishes, but it ensures that successive generations of stars are born with the gifts of their ancestors already inside. By now, it's clear that stars are not isolated points of light. They are the central actors in the great story of the cosmos. They sculpt galaxies with their collective light and their winds and explosions. They forge nearly every chemical element heavier than helium in their cores or in their fiery deaths. And they create the conditions for planets to form around them in the leftover disks of their birth. From those planets, beings like us can eventually emerge, beings made of star stuff, who then look back and ponder the stars. Our Earth coalesced around a second or third generation star, the Sun, about 9 billion years into the universe's timeline. It carries in its rocks and living organisms the fingerprints of countless stars before us. The silicon in the sand, the phosphorus in our DNA, the sodium and chlorine in the oceans, those atoms were fashioned long ago in stellar furnaces and then scattered across space, eventually to become part of this planet. The heavy elements from bygone stars now circulate in our blood and build our cities. We truly are a way for the cosmos to experience itself, as one great scientist put it. When we gaze at the stars, we are literally seeing our own origins. The light from those distant suns allowed Earth to form and life to develop, and now our eyes capture that light and our minds understand it. We have closed a loop in a sense. The stars made us, and we in turn can comprehend and appreciate the stars. It's a humbling and uplifting realization that underscores the unity of everything in the universe.
As our journey through the lives of stars comes to an end, picture yourself once more standing beneath a clear, dark night sky. The silence of the night is profound. The only sounds might be the wind or a distant owl. Above, the stars sprinkle the heavens with their gentle light. The Milky Way arches overhead, a faint band
made of the amalgamated glow of billions of distant stars. With the knowledge we have gathered, each point of light now carries a story. You can point to a star and think, that might be a middle-aged star like the Sun, with planets orbiting it and perhaps life of its own. Another might be a massive blue giant destined for a short, brilliant life and a dramatic supernova end. That red one there could be a giant star in its final phases, about to shed its husk and reveal a white dwarf. Yet another faint smudge might not be a single star at all, but an entire galaxy far beyond our own, filled with hundreds of billions of stars, each with its own journey. In the stillness of such a night, the weight of this understanding can be awe-inspiring. We stand tiny on a small planet, bathed in the ancient light of stars, connecting us to epochs and places we will never see. The stars evoke not just scientific curiosity, but also a deep emotional response. For thousands of years, humans have looked up in wonder, weaving myths and seeking guidance from the stars. In ancient times, the night sky was humanity's map and calendar. Farmers planted and harvested by the rising of certain stars. Sailors navigated by the star patterns, and every culture filled the sky with stories, images of bears, hunters, dragons, and heroes that gave meaning to those distant lights. The stars have always been our companions in the dark, symbols of permanence, even as we now know they too have life cycles. Now we have peeled back many of their secrets, yet the wonder remains, and has perhaps only grown deeper. We know that those stars are not eternal. They are born, they age, and they die, in an endless cosmic cycle. We know that on some nights, some of the stars we see have already died in reality, but their light is still on its way to us, a messenger from the past. We know that every atom in our body was once inside a star that died long before Earth formed. We are intimately connected to these points of light. They are our stellar ancestors, and in a real sense, we are their children. Such knowledge does not diminish the star's beauty, it amplifies it. When we look up now, we see not just pretty lights, but a grand story unfolding across the vastness. Eventually, even the stars will fade. The universe is dynamic and evolving. Trillions of years from now, the galaxies will exhaust their gas, star formation will cease, and the remaining stars will gradually die out. The cosmos will go dark again, as it was in the beginning, but now filled with the remnants of those stars. White dwarfs turned cold and black, neutron stars, and black holes roaming the darkness. But that far future is almost beyond contemplation. Right now, we live in a universe awash with starlight. It is the golden age of stars, where new ones still form and the night sky still gleams. We are fortunate to witness it, and as long as there are eyes to see and minds to wonder, the stars will never be merely points of light. They will be beacons of meaning, symbols of the enduring cycle of creation and transformation. Stars are the ancestors of everything we know and the architects of the universe's structure. They crafted the elements that form our world and our bodies. They organize themselves into galaxies that shape the cosmos on the grandest scales. As we conclude this meditation on stars, we find ourselves back in silence, contemplating the darkness that is now no longer empty. It's filled with the gentle glow of distant stars and galaxies, a cosmic tapestry woven by countless suns. In the great silence of space, the starlight we see continues to journey outward. Even after a star has lived its life and gone, its light remains, traveling through the darkness, carrying the tale of that star's life to faraway places. Right now, above you, photons from stars hundreds of light years away are gently landing on your eyes, having left their homes long before you were born. And those photons will continue past you into the night, on an endless voyage. The universe is silent, but it is not empty. It is filled with the stories of stars, whispered in the language of light. And so we end where we began, with darkness,
and quiet. But now we know that in that darkness, light is always traveling. The stars, our brilliant ancestors and cosmic architects, shine on, and in the quiet darkness, their light continues its eternal journey. In the silent darkness of space, their starlight continues to travel, carrying their story across the cosmos forever.